The night Mars almost spoke back. It started as just another routine pass, another clean stream of numbers and images flowing across a dark control room. Then, in less than a second, everything froze. The live feed from a rover's mass camera locked on a rust-red horizon and died. No explosion, no dramatic impact, just a silent frame of Mars under a pale, thin sky, and a hiss of static where a living signal had been a heartbeat earlier. For a while, no one moved. The thing is, Mars transmissions drop out all the time. Antennas slip out of alignment, orbiters duck behind the planet, solar storms wash over the link. Engineers are trained to wait, to assume it will come back. This one didn't. On the main screen, the last image held. A gentle slope of dust, scattered rocks, the faint outline of distant hills. It looked calm, almost peaceful. In other words, exactly like a place where nothing is happening and nothing ever will. But in the control room, the air changed. Voices went low. Chairs rolled closer to consoles. Hands hovered over keyboards as status lights shifted from green to amber, then to a flat, accusing red. Telemetry vanished first, then the heartbeat tones, then the backup channel through the relay orbiter. One by one, every path that connected that lonely machine to Earth went dark, as if something on that empty plane had just swallowed the signal whole. The scary part is, this was not new. Mars has been doing this for decades. Over a third of all missions sent there have failed. Orbiters have burned up in the atmosphere. Landers have smashed into the ground. Some, like entire Soviet craft in the 1970s, simply stopped talking and never said why. Engineers even have a nickname for it: the Great Galactic Ghoul, an imaginary creature that eats Mars probes. On this night, the team watching that frozen horizon knew that history. They also knew what would have happened if this rover was gone. Years of planning, hundreds of millions of dollars, and a once-only chance to sample a specific region that might preserve traces of ancient water, erased in a single glitch. Here is where things get uncomfortable. What disturbed investigators most was not what they saw on that final frame. It was what they realized later they had almost seen. In the minutes before the signal died, the rover had been turning its instruments toward a subtle chemical anomaly in the soil, a patch that looked, to its sensors, just a little too different from the dust around it. The result was a flurry of last-second commands, tiny adjustments, a camera beginning to tilt down. Then nothing. Eventually, the image logs were reconstructed second by second right up to the cutoff. The incredible part was how close the system came to sending one more picture, one more frame from just a slightly lower angle. Whatever would have been in that shot never reached Earth. And that is the pattern. Mars lets some data through, it buries the rest. Because this planet is not just a destination on a star chart, it is a graveyard of broken machines, a failed Earth that once had oceans and an atmosphere, and possibly a silent warning about where worlds like this and worlds like ours can end up. Mars looks beautiful through a telescope. Up close, it starts to look like the perfect place to die slowly. This episode is a guided tour through that contradiction. A planet that has inspired centuries of dreams, and at the same time, a place that quietly destroys machines, erases evidence, and exposes how fragile human technology really is. Engineers even gave it a nickname: the Great Galactic Ghoul. On paper, that sounds like a joke. In practice, it reflects a very real pattern. More than a third of all missions sent toward Mars have failed. Some vanished during approach. Some broke apart in the thin atmosphere. Some crashed directly into the surface. The thing is, these were not amateur experiments. These were national flagships, billion-dollar projects, the best hardware entire countries could build. The Mars Climate Orbiter in 1999 is one of the most disturbing examples. It was lost because one team used metric units and another used imperial, a simple conversion error. The result was a spacecraft entering the atmosphere at the wrong angle and burning up. In other words, a planet 225 million kilometers away punished a tiny mistake made on a screen on Earth. And the scary part is, the ghoul does not just eat machines. It may have eaten an entire ocean. Evidence from orbiters and rovers points to a Mars that once had rivers, lakes, maybe even a northern ocean, rounded pebbles that only flowing water can make, layered sediments that look uncannily like dried up deltas. For a while, it might have been almost Earth-like, with a thicker atmosphere and a global magnetic field. Then something happened. The magnetic field collapsed. The atmosphere thinned. Solar radiation began stripping gas away into space. Over millions of years, the planet entered a slow-motion death spiral. What would have happened if that process had started on Earth instead? Here is where things get uncomfortable. The basic physics is the same. A world loses its shield, and space takes everything back. Mars lost its magnetic field. Its core cooled 4 times faster than Earth's due to its smaller mass, killing the dynamo by 4.1 billion years ago. The solar wind came and stripped the atmosphere away, 100 grams per second, the equivalent of an Empire State Building's worth of air every century. But it wasn't uniform. The day-side ionosphere lost ions 10 times faster than the night side, creating wind shadows. And the process was brutal. Not a slow fade, but a catastrophic collapse during the Hesperian transition. A magnetic death that happened over millennia, not eons. By then, Mars's escape velocity of 5.03 kilometers per second meant the lighter molecules, hydrogen, helium, had already fled. What remained was denser, heavier, and increasingly hostile. But it wasn't uniform. The ionosphere itself was asymmetrical. The day side lost ions 10 times faster than the night side due to solar radiation pressure, creating a wind shadow effect on the dark side. Mars was being torn apart unevenly, like a body exposed to fire on one side and left frozen on the other. This video will move through that story piece by piece. First, the graveyard of lost spacecraft and strange failures that earned Mars its monstrous nickname. Then, the evidence for ancient oceans and a climate collapse that turned a blue world into a frozen desert. After that, the focus shifts to what Mars would actually do to human bodies. Constant radiation from cosmic rays and the sun. Toxic dust laced with perchlorates that can disrupt thyroid function and infiltrate lungs, habitats, and equipment. The incredible part was how quickly scientists realized that the air not being breathable is only the beginning of the problem. From there, the path leads into stranger territory. Unexplained methane spikes, odd lights in rover images, eerie sounds carried through a whisper-thin atmosphere. Finally, it reaches the most disturbing question of all. Should humans try to terraform this place? And what does it mean to remake a dead world in Earth's image? By the end, Mars will not look like a romantic frontier. It will look like a warning, playing out in slow motion on the sky's red dot, showing where a planet can go when its luck runs out. For a while, that red warning light in the sky was anything but disturbing. Through early telescopes in the 19th century, Mars looked less like a dead world and more like a distant mirror of Earth. The views were terrible by modern standards. small fuzzy disks, pale orange deserts, dark patches that seem to shift with the seasons. Astronomers watched these markings brighten and fade and assumed they were seeing seas, continents, even vegetation breathing in and out across a Martian year. Then came the lines. In 1877, Italian astronomer Giovanni Schiaparelli reported seeing long, straight streaks crisscrossing the planet. He called them canali, channels. In other words, natural grooves or striations. But in English, canali became canals. And that one translation error opened the door to something far more dramatic. Percival Lowell walked straight through it. At his private observatory in Arizona, Lowell stared at Mars night after night and sketched what he thought he saw. A vast geometric web of canals, hundreds of them, connecting dark oases at the poles and equator. To him, these weren't accidents of geology. They were engineering. Lowell became convinced that Mars was a dying world, its oceans long gone, its air thinning, its last inhabitants fighting back against extinction. The thing is, he imagined a planet-spanning irrigation system built by intelligent beings to drag the last trickles of polar ice toward the equator. For a while, many scientists took this seriously. The incredible part was how specific the fantasy became. Books and newspapers described noble Martian civilizations calmly managing their own climate collapse. Early science fiction followed, filling Mars with ancient cities, crystalline towers, and wise, fragile beings watching a red sun sink over dusty canals. Here is where things get uncomfortable. Strip away the crystal towers, and that picture of a world clinging to life on a drying planet was closer to reality than anyone realized. Mars did lose its oceans. It did lose its thick atmosphere. It did face a slow-motion planetary death. They had no idea how right they were about the ending, and how wrong they were about everything in between, because when spacecraft finally arrived, the result was brutal. Mariner 4 in 1965 sent back the first close-up images. No canals, no cities, just impact craters and a sky the color of butterscotch over an airless, frozen desert. Later missions revealed an atmosphere less than 1% of Earth's, surface radiation strong enough to damage DNA, and dust laced with toxic perchlorates. The romantic Martians vanished overnight. The scary part is the emotional whiplash. A planet once imagined as a wiser, older neighbor turned out to be a silent graveyard with dried riverbeds and empty basins where oceans once stood. The dream of meeting someone on Mars was replaced by the question of what would have happened to anything that ever lived there. And yet, the story still wasn't finished, because as later orbiters and rovers dug deeper into that wasteland, they uncovered something even more disturbing than the lost canals. Evidence that Mars had been alive with water, and then something happened. There was water once, liquid water. Jarosite crystals found in Meridiani Planum prove it. Iron sulfate minerals that form in acidic conditions, which means the water wasn't neutral. It was hostile, acidic, the kind of water that dissolves certain minerals and corrodes certain structures. If life emerged on Mars, it would have emerged in a chemical environment fundamentally different from Earth's oceans. We don't know if that's a barrier to life or merely a different pathway. We simply don't know. The minerals tell us about the water. Clay minerals, phyllosilicates, suggest neutral to slightly alkaline conditions, pH 7 to 8. But sulfate minerals suggest acidic water, pH 3 or lower. These aren't found in the same locations. Different regions of Mars had different water chemistry. One part of the planet had habitable oceans. Another had acidic lakes. This isn't a simple story of Mars had water, then lost it. It's a story of chemical heterogeneity, regions with vastly different conditions existing simultaneously, like Earth having oceans in one hemisphere and acid baths in the other. If life emerged on Mars, it emerged in multiple chemical regimes, or adapted across them. Mars had been alive once, but before scientists could even begin to understand what had happened to it, something else started to become clear. The planet was not just a dead world, it was a ship killer. In the early 1960s, as the space race pushed outward, both the United States and the Soviet Union set their sights on Mars. Rockets rose from Baikonur and Cape Canaveral loaded with fragile probes, early cameras, and high expectations. For a while, it looked like the next logical step after the moon. Then the failures began. Soviet engineers launched a series of Mars probes with names like Mars 1, Mars 2, MV, and Zond. Some never even made it out of Earth orbit. One booster lost thrust and fell back into the atmosphere. Another suffered a guidance failure, tumbling until it tore itself apart. In other words, the missions died before they ever even saw Mars. The scary part is that the ones that did escape Earth did not fare much better. Mars 1 headed outward in 1962 and then simply went silent, its radio link fading into static long before arrival. Later, Mars 2 and Mars 3 in the early 1970s actually reached the planet. Mars 2's lander slammed into the surface at high speed. Mars 3's lander touched down, transmitted for about 20 seconds, and then never spoke again. American attempts were not immune. Early Mariner launches failed on the pad or in the first minutes of flight, destroyed by rocket malfunctions that turned entire missions into brief, bright fireballs over Florida. Even later, more capable orbiters were lost. The Mars Observer in 1993 was 3 days away from entering orbit when contact suddenly dropped and never returned. Here is where things get uncomfortable. After enough of these disappearances, engineers started to joke that something out there was eating Mars missions. They gave it a name: the Great Galactic Ghoul, a mythical creature that supposedly lurked along the Mars trajectory, feasting on spacecraft that got too close. On the surface, it was dark humor, a way to laugh in control rooms that had just watched years of work vanish in a single line of flat telemetry. But behind the joke was real anxiety. Over a third of all missions ever sent to Mars have failed, making it one of the most unforgiving targets in the solar system. The incredible part was how ordinary many of the causes looked on paper: valve leaks, wiring faults, software errors. One later mission, the Mars Climate Orbiter, was lost because one engineering team used imperial units while another used metric, a simple mismatch that ended with the spacecraft dipping too low and burning up in the atmosphere. Yet not every case had such a neat explanation. Some orbiters went silent with no clear hardware culprit. Some timing coincidences, like failures right at critical engine burns, left gaps in the data that still bother people who worked on them. It is pretty disturbing to realize how often the official answer is simply that something happened, and the result was total loss. And this raises a different question. If Mars does this much damage to machines that only have to survive for a few years, what would have happened to human crews trying to live there for decades? Because the planet does not just destroy spacecraft in transit. Once anything reaches the surface, an entirely new set of threats begins. The thing is, not every disaster on Mars comes from the planet itself. Sometimes the most disturbing damage starts in a quiet office on Earth. In September 1999, a spacecraft called the Mars Climate Orbiter arrived at the Red Planet. On paper, it was a modest, almost routine mission. Its job was to study Martian weather, track dust storms, measure how the atmosphere changed over time, and act as a relay station for other spacecraft that would follow. In other words, it was supposed to be the calm, dependable communications hub in orbit, a kind of traffic controller for a growing robotic presence around Mars. For a while, everything looked normal. The spacecraft had launched successfully, cruised through interplanetary space for nearly 9 months, and was approaching Mars on schedule. Controllers at NASA's Jet Propulsion Laboratory watched the numbers stream in. The trajectory solutions, the predicted altitude for orbital insertion, the expected path through the thin Martian air. They had no idea that something very small and very human had already doomed the mission. Hidden inside the software that calculated the tiny thruster firings was a mismatch. One engineering team was working in imperial units using pound-seconds of force. Another team, following NASA standards, expected metric units in Newton seconds. The numbers looked fine. The math ran. The result was trusted. Here is where things get uncomfortable. Nothing about Mars had changed. The planet was exactly where it was supposed to be. The spacecraft's instruments still functioned, but every time the orbiter adjusted its course, the error compounded. The trajectory being fed into mission planning was subtly wrong, pulling the spacecraft lower and lower than anyone realized. On September 23rd, during orbital insertion, the Mars Climate Orbiter slipped behind the planet as expected. Radio contact was supposed to drop out briefly, then return once the spacecraft emerged on the other side in a stable elliptical orbit. The signal never came back. Controllers waited. Antennas swept the region of sky where the spacecraft should have appeared. Commands were sent. Silence. Eventually, analysis suggested what had happened. Instead of skimming safely through the upper atmosphere, the orbiter had dipped far too low, likely tearing apart or burning up in the thin but still deadly Martian air. The scary part is that Mars did not kill this mission in any active sense. $125 million spacecraft, years of work, and a critical piece of Mars infrastructure were destroyed by a unit conversion error that went unnoticed in human communication. The incredible part was how mundane it all seemed on paper. A mismatch between pounds and newtons. A software interface document not fully checked. Yet the result was total loss. Another piece of hardware added to Mars's invisible graveyard. It is pretty disturbing that this failure at least had a clear explanation. Engineers could point to a line in a report and say, "This is what went wrong." Around Mars, not every disappearance is so neat. Some spacecraft simply vanish into the radio noise, leaving only fragments of data and unanswered questions about what really happened out there. Around Mars, silence is not empty. It often arrives in a single frozen line of data, and it usually means something has just died. In August 1993, engineers on Earth were watching the Mars Observer cruise toward its destination after an almost flawless journey. The spacecraft was days away from firing its engine and slipping into orbit. Telemetry looked clean. Temperatures, voltages, guidance numbers, all well within limits. Then, in a span of seconds, the data stream went flat. No dramatic spike, no clear final error code, just a sudden loss of signal right before a critical maneuver. For a while, controllers tried to convince themselves it was a simple communications glitch. Antennas were checked, commands were resent, backup receivers were brought online. Nothing answered. The scary part is that Mars Observer is not unique. Missions like the Soviet Mars 6 lander, the Russian Mars 96 spacecraft, and later the European Schiaparelli lander all failed either just before or during their most dangerous phase near Mars. In other words, they died exactly when information is needed most. The result was the same haunting pattern: normal telemetry, rising tension, and then a clean cut to silence. Here is where things get uncomfortable. On Earth, a plane crash leaves debris, burn marks, twisted metal that investigators can touch. Around Mars, almost nothing is ever recovered. Most of these machines are now scattered across valleys, slopes, and dust plains that no one has seen in detail. Scientists are left with a few minutes of radio data and a long list of maybes. For Mars Observer, the leading explanation is a fuel leak. A tiny rupture in a pressurized line could have vented propellant, spun the spacecraft out of control, and forced its computer into a fatal tumble. Other missions may have suffered stuck valves, frozen regulators, or software that misread sensor noise as real motion and fired thrusters in the wrong direction. These are all plausible technical causes. The thing is, almost none of them can ever be confirmed. The incredible part was how ordinary the last numbers often look. Voltages steady, attitude stable, no obvious alarms. Then the carrier signal fades, and that is the final record of a machine that cost hundreds of millions of dollars and years of human effort. Engineers replay those last seconds again and again, asking the same question: what would have happened if one line of code, one valve, one timing sequence had been different? Over time, this has given Mars an unsettling reputation among mission teams. A joking nickname emerged: the Great Galactic Ghoul that eats spacecraft. But underneath the humor is something pretty disturbing. This is a world where failures become ghost stories, supported only by partial logs and half-understood glitches. Eventually, future rovers and orbiters might image some of this wreckage in high enough detail to solve a few of the mysteries. Until then, Mars remains a planet wrapped in lost signals and unmarked graves of metal. And that raises a different question. If this is what happens to machines, what happens when the thing going silent on Mars is human? So imagine the camera pulling straight up from the rust-red dust. The view stops being a landscape and turns into a map. An overhead chart of Mars, the whole planet flattened out, and then the dots start to appear. Each dot is a failure. In the northern plains, a marker flashes where Soviet engineers tried again and again to be first. Mars 2 in 1971, hitting the atmosphere too steeply and slamming into the ground. Mars 3, landing softly and sending a signal for less than a minute before going silent forever. For a while, no one even knew exactly where the wreckage lay. Shift west, another cluster, the Soviet Mars 6 and Mars 7 landers, one losing contact during descent, the other missing the planet entirely. The thing is, each of these dots is years of work, thousands of people, and entire careers ending in a few confused seconds of telemetry. Zoom in on another scar. 1999 Mars Climate Orbiter. It never even reached the ground. A simple unit conversion error between metric and imperial sent it plunging too low, and the result was a $125 million spacecraft disintegrating in the atmosphere. The scary part is that tiny mistake is now just another invisible point on this mental map with no wreckage anyone can visit. Near the equator, more recent debris appears. The Schiaparelli E DM lander, a joint European effort in 2016, firing its thrusters too briefly, cutting off early, and smashing into Meridiani Planum at over 300 kilometers per hour. From orbit, scientists later saw a dark stain on the dust, a parachute, and a backshell lying nearby like discarded trash. In other words, the last frame of a very expensive accident. Now the camera sweeps across the planet and the pattern becomes disturbing. Parachutes frozen in place, heat shields half buried, backshells scattered like bones. Even the successful missions leave fragments behind, shells and covers and dead descent stages that will never move again. Here is where things get uncomfortable. The glossy Mars seen in press images is carefully framed. Clean horizons, untouched dunes, a pristine alien frontier. But laid out as a map, Mars looks different. It starts to resemble a slow-motion scrapyard, a world quietly accumulating technological corpses from half a century of attempts to reach it. Every silent rover on that map once sent back hopeful first images. Opportunity, designed for 90 days, finally buried in dust. Spirit trapped in soft soil until its power faded. Pathfinder's Sojourner, motionless beside a dead lander. The incredible part was how long some of them lasted. The disturbing part is how abruptly they all became just more dots. So what happens when this map keeps filling in? When future colonists look out across the plains and see not an untouched world, but a landscape haunted by hardware that never came home. For one rover, that haunted landscape was home for almost 15 years. Opportunity landed in 2004 in a small Martian crater with a simple assignment and a short expiration date. 90 Martian days. That was all it was designed for. Thin wheels, modest instruments, solar panels that were never meant to endure more than one harsh season. The result was very different. The rover drove more than 45 kilometers, found evidence of ancient water, and outlived its twin, Spirit, by years. It became less like a disposable tool and more like a quiet resident of Mars. Engineers gave it wake-up songs. Scientists talked about its health and mood. For a while, it felt endless. Then, in mid-2018, the sky began to thicken. It started as a regional dust storm. These happen on Mars when sunlight heats the ground, lifting fine particles into the air. But this one grew. Dust climbed higher, spread wider, and the storm began to wrap around the planet. In a matter of weeks, daylight at Opportunity's location in Perseverance Valley faded into a dim orange twilight. The thing is, Opportunity depended entirely on the sun. No nuclear power source, no backup generator. Its life was stored in its batteries, and those batteries needed light. As the dust thickened, the rover's solar panels produced less and less energy. Engineers watched the power readings drop day after day. Here is where things get uncomfortable. Mars dust is not like a brief Earth dust cloud. The particles are tiny, electrostatically clingy, and can stay suspended for months. The atmosphere is thin, but once dust gets up there, it can circle the globe and turn the entire planet into a muted, choking haze. This was not a passing storm. It was a slow suffocation. By June, the sunlight at Opportunity's site had fallen to levels that would be like trying to run a house on a solar panel during a total eclipse. The rover sent one of its last power reports, then a final haunting signal, a transmission indicating that its batteries were critically low and the sky was dark. The scary part is how long the silence lasted. After that final contact on June 10th, NASA kept calling. Commands were sent for months through summer and into early 2019 in case the dust settled and the panels cleared just enough to let the rover wake and phone home. They had no idea if it was already frozen or just barely hanging, on in the cold. Eventually, nothing answered. The incredible part was that the rover itself likely did not fail in any dramatic way. No explosion, no crash, just a gradual loss of power until its electronics slipped below survival temperature. In other words, Mars simply outlasted it. Today, opportunity is still there, intact, motionless, under a thin veneer of dust on a silent plain. It is a complete machine in a place that no longer cares whether it functions or not. And if future colonists ever reach that valley, what would it feel like to stand beside that frozen rover and realize how gently and how completely this planet can turn things off? Because Mars does not always kill with impact or radiation. Sometimes it just takes away the light and waits. Mars waits. But the scary part is, it did not always wait in silence. For a while, the planet that now smothers rovers in dust may have been something else entirely. Here is where things get uncomfortable. What if the most disturbing thing about Mars is not the wreckage humanity has lost there, but what Mars itself lost first? From orbit, high-resolution images show something unsettling. Winding channels snake across the surface, branching and merging the way rivers do on Earth. These are not random cracks. They look like dried-up river valleys, carved by flowing water that ran for a very long time. The habitability didn't last. Something changed. But it wasn't gradual. The Noachian period, 4.1 to 3.7 billion years ago, was wet. The Hesperian period, 3.7 to 2.9 billion years ago, shows a rapid transition, not a slow decline, but a collapse. Over a span of 100,000 to 1 million years, Mars went from having sustained surface water to being essentially dry. That's not geological time. That's almost rapid on a planetary scale. It suggests not a gradual weakening of the magnetic field, but a catastrophic failure. One moment, protective. Next moment, exposed. The timing aligns with solar wind stripping, but we're still uncertain about the exact mechanism. What we know is this: Mars's death happened fast enough that if life had emerged, it might have emerged just in time to experience its planet dying. Near some of these valleys, fans of debris spread out into broad, triangular shapes. On Earth, that pattern appears where rivers slow down and drop their sediment into lakes or seas. Scientists call them delta fans. On Mars, they sit in the basins of ancient craters, as if those craters once held deep, persistent lakes. The incredible part was what showed up at a much larger scale. Along certain regions, subtle ridges and terraces trace long, looping arcs for hundreds of kilometers. To the naked eye, they look like faint scars. In other words, they resemble shorelines, the edges of something vast and heavy that pressed against the land for millions of years. Taken together, the result was a picture that is pretty disturbing. Billions of years ago, Mars seems to have had rivers, lakes, and maybe entire oceans, a thick atmosphere, clouds, rain, a blue world colder than Earth but strangely familiar, with liquid water moving across its surface under an open sky. If that is true, then another question follows: what would have happened on a world like that given enough time? On Earth, where there is long-lived liquid water, life appears quickly and refuses to leave. For Mars, there are hints: certain minerals that form only in standing water, layered sediments that look like they were laid down at the bottom of ancient lakes, and occasional spikes of methane in the thin air above. On this planet, methane is often linked to biology. On Mars, its source is still unknown. It fades, then returns, as if something underground exhales in brief, quiet bursts. Scientists are careful, but the pattern is hard to ignore. Then something happened. The atmosphere thinned, the rivers cut off. Any oceans, if they existed, receded and froze. The planet's magnetic shield weakened or vanished, and the sun's radiation began stripping away the air, molecule by molecule, until the sky itself failed. Today, Mars is red, dry, and nearly airless. But every valley, every delta, every possible shoreline is a reminder that it did not die all at once. It suffocated. And eventually, this raises a different problem. If an entire planet can slowly lose its air and its water, how does that process start? And how far can it go? In the next section, the story turns from ancient lakes to planetary collapse and what a long, quiet death like Mars's might imply for Earth's future atmosphere. Mars looks empty now, but its surface still remembers when it was loud with water. From orbit, the planet is covered in scars that should not exist on a dry world. Satellite images show branching channels that split and rejoin like tree limbs pressed into stone. First, they look like old riverbeds on Earth. Then the resolution sharpens, and the resemblance becomes disturbing. Some of these networks, such as those in the Margaritifera Terra region, sprawl for hundreds of kilometers. They curve, meander, and merge exactly the way liquid flowing downhill would carve them. The thing is, wind does not do that. Lava does not do that. Only sustained running water cuts landscapes into branching veins on that scale. Elsewhere, entire canyons slice across Mars. Valles Marineris is the most extreme example. It stretches more than 4,000 kilometers, longer than the distance from New York to Los Angeles, and drops deeper than the Grand Canyon by a factor of 4. It looks less like a crack and more like a continent-scale flood channel frozen in mid-collapse. Then there are the layers. Craters and basins in places like Gale Crater and Jezero are ringed with stacked, fine bands of rock. From orbit and from rover cameras, they resemble the sedimentary layers at the bottom of dried lakes on Earth. Thin sheet after thin sheet laid down quietly over time. In other words, not a brief flood, but water that stayed. The rocks themselves tell the same story. Rovers have found clays, which form when water lingers long enough to alter volcanic minerals. They have also detected sulfates that precipitate from evaporating water. These minerals are concentrated in ancient basins and deltas, exactly where long-standing lakes and shallow seas would have pooled. For a while, scientists tried to explain this away with brief, violent episodes of melting, but the distribution of clays and their thickness forced a different conclusion. The incredible part was that the chemistry suggested oceans of time, not just oceans of water. That leads to the most unsettling idea of all: a northern ocean. The low, smooth plains of the Martian north sit a few kilometers below the southern highlands, forming a natural basin the size of North America. Along the boundary, orbiters have traced faint, looping contours that look suspiciously like ancient shorelines. If those lines really mark an ocean edge, the numbers become scary. Models suggest an ocean that could have covered up to a third of the planet, with depths in places rivaling the Mediterranean. Imagine the Pacific pulled up and poured into a single cold bowl. Here is where things get uncomfortable. Rivers longer than the Nile, basins as wide as countries, and a global ocean basin do not belong on a dead desert. They belong on a world that, for millions of years, was wet, relatively thick-aired, and stable enough to be genuinely habitable at the surface. The scary part is what happened next. Because if Mars could go from oceans and clay-rich deltas to a frozen graveyard, the next question is not just how it died, but what would have happened to anything that tried to live there. Mars didn't die in a single impact or a sudden flare. It died the slow way, from the inside out. Early Mars probably looked strangely familiar. A hotter interior kept its metallic core molten and churning. That motion created a global magnetic cocoon, a protective bubble around the planet very similar to Earth's. In other words, there was once an invisible shield standing between Mars's sky and the sun. For a while, that shield held. The thing is, small planets lose heat fast. Over hundreds of millions of years, Mars's core cooled and stiffened. The internal engine that drove its magnetic field sputtered, then faded. The global shield fragmented into weak patches, and then almost nothing at all. Here is where things get uncomfortable because that is the moment its atmosphere was effectively handed over to the sun. The sun does not just shine, it blows. A constant gale of charged particles races outward in every direction. This is the solar wind. Around Earth, the magnetic field grabs and redirects most of it, forcing it to flow around the planet like water around a rock. On a nearly unshielded Mars, that same wind could slam directly into the upper atmosphere. The result was not a dramatic blast, but a relentless sandblasting. Lighter molecules like hydrogen and helium were the first to be stripped away. Then oxygen and carbon dioxide at the fringes began to go as well, one particle at a time, one molecule at a time. The scary part is how patient that process can be. Over billions of years, a thick, potentially warm atmosphere can be erased without a single obvious event to point to. NASA's MAVEN mission was sent to measure exactly how this works. Since 2014, it has been flying through the fringes of the Martian sky, watching the solar wind peel ions away and fling them into space. MAVEN has seen atmospheric particles literally streaming down the planet's magnetic tail. It has recorded how that loss rate jumps during solar storms. Scientists can take those numbers, run them backward in time, and reconstruct a disturbing picture. Today's thin air is just the leftover scrap of something once far more substantial. The solar wind came. It still comes. Right now, Mars loses approximately 100 grams of atmosphere per second, a number that sounds small until you calculate it. 3,155 metric tons annually. Over a century, that's roughly the mass of the Empire State Building. Over 1 billion years, entire oceans worth of air simply escaped into space. As the air thinned, surface pressure dropped. Liquid water, which had pooled in basins and carved valleys, reached a tipping point. Under such low pressure, it could no longer stay liquid for long. It boiled away into the already failing sky, or froze into the ground and polar caps. Eventually, the oceans vanished, not because they were used up, but because the planet lost the blanket that made them possible. Mars, in effect, suffocated, not in minutes, but over ages. A world that could host rivers and maybe even shallow seas had its breath-stolen molecule by molecule until only a cold, whisper-thin atmosphere remained. And the incredible part was, the killing never really stopped. MAVEN shows it is still happening today. The disturbing question now is simple. On a planet that can lose an entire sky, what chance does anything fragile have on the surface? So imagine that stolen sky coming back. Just for a moment, rewind the tape of Mars and press play on a different world. The planet turns slowly in the dark, but this time it is wrapped in a thick, deep blue atmosphere. Clouds swirl in bright white bands. Sunlight catches on long, winding rivers that glint like metal, and on broad, shallow seas that breathe mist into the air. The surface is not the dead rust seen in modern images. It is dark basalt, wet shorelines, deltas fanning out where water slows and drops its load of sediment. From orbit, storm systems roll across the planet, casting moving shadows over coastlines that no longer exist. For a while, it looks disturbingly familiar, almost like a colder, smaller Earth. Then the time lapse starts to accelerate. The planet spins faster, days flickering by in seconds. The blue begins to thin. Clouds break apart. The color drains from the sky until it turns pale, then washed out, as if someone is slowly erasing the atmosphere with invisible hands. Rivers that once carved valleys shrink. They pull back into narrower, darker threads, then into scattered lakes, then into isolated, stagnant pools. Eventually, even those pools vanish, leaving behind dark, branching scars across the surface. In other words, the map of water turns into a fossil. Here is where things get uncomfortable. Dust begins to rise. At first, it is local, small storms kicking up in basins and craters. Then the storms grow taller, more violent, reaching higher into the thinning sky. In the sped up view, pale orange veils race around the planet, merging into walls of dust that swallow continents. The atmosphere starts to bleed away. A faint, ghostly halo glows at the edge of the planet, like a thin ring of escaping light. Those are molecules being stripped into space, swept away by radiation and the solar wind. The result was a slow suffocation on a planetary scale, a process so gradual that no single day would have felt like a disaster, but the end state is catastrophic. Temperatures fall. Frost creeps outward from the poles, bright white fingers sliding into lower latitudes. Ice locks into the ground, hiding in shadows and burying itself under dust. The blue fades completely. The sky shifts to a pale, sickly tan, then to the familiar salmon color seen in Rover. Panoramas. The scary part is how ordinary the final frame looks now. A cold desert, a thin, tired atmosphere, dust devils twisting lazily over empty plains, dry river beds frozen in place for billions of years, their curves and deltas still visible, but lifeless. Fossil shorelines trace the edges of vanished seas, like outlines around a crime scene. Pause the time lapse there. This is the Mars that orbiters and rovers send back in high definition. Beautiful but pretty disturbing when played against its own past. Scientists look at those dried channels and layered sediments and see a warning written in stone. Planets can change. Habitability is not a permanent setting. It is a temporary condition. And the disturbing question now shifts again. If one world can quietly cross a line from ocean-bearing to airless desert, how certain is it that others, including the one under human feet, will always stay on the safe side of that line? Habitability is not a permanent setting. The disturbing question now becomes even sharper. If Mars once had oceans, what moved in those waters? And what happened to it? On Earth, long-lasting liquid water almost never stays empty for long. Give it energy, the right chemistry, and enough time, and life appears to be less an exception and more an outcome. Deep sea vents, boiling hot springs, buried furs under Antarctic ice. The result was always the same. Microbes found a way. But there's a possibility we're missing. Subsurface aquifers may still exist 1 to 5 kilometers underground, fed by geothermal heating in volcanic regions. Mars isn't cooling uniformly. Pockets of the crust remain hot. Water might still flow in the deep subsurface, not ancient relics, but active aquifers. And if water persists, and if life ever emerged on Mars, that life might still be there, not on the surface, not in any rover's reach, but alive in the dark, in thermal vents 3 kilometers below, in conditions we can barely imagine. We have no instrument that can detect subsurface microbes. We have no way to sample what's happening a kilometer down. When we say Mars is dead, we mean the surface is dead. We have no idea what's happening below. Mars lost its water. The deuterium to hydrogen ratio, D/H, tells us how much. Mars's D/H is 5 to 6 times higher than Earth's, a signature of preferential hydrogen escape. Light hydrogen molecules, H2, escaped to space. Heavy deuterium, heavy hydrogen stayed behind, concentrating in what remained. By working backwards from current D/H ratios, we can estimate Mars's original hydrogen inventory. The calculation is sobering. Mars once had an ocean roughly 4 kilometers deep, covering much of the planet. 4 kilometers? Earth's average ocean depth is 3.7 kilometers. Mars, a smaller planet, had oceans as deep as Earth's. Then it lost them all, not to impacts, not to freezing, to escape, to the solar wind. The planet was stripped. Mars had many of the same ingredients: thick atmosphere, stable rivers, possibly entire northern oceans lasting tens or hundreds of millions of years. In other words, it had the conditions that, on Earth, are almost offensively good at producing biology. The scary part is that if those conditions did not give rise to anything living, it forces a disturbing recalculation about how fragile the spark of life really is. For a while, there were even hints that Mars might have left behind tiny corpses in stone. In 1984, a meteorite was picked up in Antarctica. Later analysis showed it had come from Mars, blasted off the planet by an impact long ago and eventually falling onto Earth's ice. Inside that rock, called ALH 84001, scientists found strange, worm-like microstructures and tiny mineral grains arranged in ways that, at first glance, looked eerily biological. Some researchers argued these were fossil microbes. Others pointed to contamination, unusual chemistry, or artifacts of how the rock had been processed. The incredible part was how fierce the debate became. Decades later, there is still no consensus. Each new technique seems to explain one feature and raise questions about another. Here is where things get uncomfortable. If those features are not life, then Mars has been silently throwing rocks at Earth for billions of years with no trace of biology in them. If they are life, then Earth has been quietly sharing a solar system with a second genesis. Modern missions are trying to settle this more careful, like Curiosity and Perseverance are. Crawling across ancient lake beds, drilling into finely layered mudstones that formed in standing water. Cameras and spectrometers search for biosignatures, organic molecules, subtle patterns in carbon isotopes, textures in rock that on Earth are produced by microbial mats. Rovers die. Opportunity died during the dust storm of 2018. But the danger isn't just the storm itself, it's the seasonality. Mars has a dust devil season in spring, where convective vortices form and climb to 12 kilometers high. When these pass over solar panels, power drops 50 to 90% for weeks. Opportunity's final message came during such a season. The rover's last transmission: "My battery is low and it's getting dark." Dark because dust devils had blocked the sun. Opportunity was waiting for the dust to clear, its battery slowly draining. It waited, and eventually the battery died. The rover is still there, preserved in Martian dust, waiting for a dust storm to clear that may never come. The thing is, both possible outcomes are pretty disturbing. If clear evidence of past life turns up, then life is not unique to Earth. It emerges wherever conditions sit in the right window long enough, which raises its own question. What would have happened on Mars if the climate had held? But if those lake sediments stay stubbornly sterile, if every drilled core is only chemistry and never biology, then the message is darker. It suggests life may require an even narrower set of coincidences than expected, and that entire oceans can come and go without anything ever learning to divide. So, what is Mars ultimately? A failed experiment in life, frozen just short of success, or a world where something microscopic still clings on deep underground, hiding from radiation and cold, waiting for the first drill or habitat to finally expose it. If anything is alive on Mars right now, it is almost certainly hiding from the sky. The open plains and rust-colored dunes look quiet in rover images, but to biology, the surface is closer to a slow-motion sterilization chamber. With almost no global magnetic field and only a whisper-thin atmosphere, Mars is bombarded by cosmic rays and solar particles. It is radiation that on Earth would be mostly stopped high above the ground. On Mars, it slams straight into the soil. The result was measured directly by the Curiosity rover's radiation detector. A human standing unshielded on the surface would accumulate a career's worth of exposure in a single extended mission. For microbes, especially fragile surface dwellers, that constant barrage is devastating. Combine that with air pressure so low that liquid water boils away in temperatures that can swing by tens of degrees in a single day, and the picture is clear. The upper few centimeters of Martian soil are hostile in almost every way that matters. But go down just a little, and the story changes. Just a few meters underground, temperatures fluctuate less, radiation levels drop dramatically, and any ice or salty liquid trapped in pores between grains might persist for millions of years. In other words, the crust itself becomes a shield. The scary part is that this is exactly the kind of environment where life could quietly endure, completely invisible from orbit. Orbiters have already mapped vast subsurface ice deposits at high latitudes, enough frozen water to cover the entire planet in a shallow ocean if melted. Radar instruments have hinted at layered ice beneath dusty plains, and in 2018, a bright radar reflection under the south polar cap was interpreted as a possible buried lake, a stable body of briny water trapped under ice. For a while, scientists argued about what would have happened if that signal was just unusual rock. Either way, it showed that the underground is not simple. Then there are the recurring slope linnae, those thin, dark streaks that appear seasonally on steep crater walls and then fade. They were first thought to be liquid water trickling downslope. Later, work suggested dry dust flows. Here is where things get uncomfortable. Even if they are not pure water, they might still involve brines seeping through the shallow subsurface, hinting that something is moving beneath the crust, cycling, freezing, and thawing. On Earth, places like that are not empty. Deep underground, kilometers below the surface, entire ecosystems live off chemical energy alone, feeding on hydrogen, sulfur, or iron instead of sunlight. At hydrothermal vents, on the seafloor, life clusters around black smokers in total darkness, powered by chemistry from the planet's interior. The incredible part was that when these communities were first discovered, they forced a rewrite of what habitable really means. If Mars ever hosted microbes, the thing is, this kind of deep, sheltered niche is exactly where their descendants might still be. Protected from radiation, insulated from the worst of the cold, feeding slowly on rock-water reactions. Pretty disturbing considering how humans plan to interact with the planet. Future missions talk about drilling meters, then tens or hundreds of meters down. Colonists imagine burying habitats or melting ice for water. They had no idea at first that every drill core and melted ice block could be punching into a native biosphere that has never seen complex life, let alone heavy machinery. What would have happened on Earth if the first industrial activity had started directly above one of those deep, fragile ecosystems? On Mars, the risk is not just contamination from Earth organisms spreading into Martian rock. It is also the possibility of waking something up or wiping something out before it is even confirmed to exist. For mission planners, this turns engineering questions into ethical ones. How deep is safe to drill? How clean is clean enough for a lander or a human base? And if the only surviving Martian life is clinging on in a few buried pockets, does humanity have the right to reshape the planet around it? The scary part is that the push to colonize Mars is accelerating faster than the ability to answer those questions. While the surface looks empty, the real story may be written in the dark, frozen rock below, in chemistry that has been running quietly for billions of years. And if that underground world exists, the next disturbing question is simple. What happens when human plans start to compete directly with whatever is already there? For a while, that sounds like harmless chemistry. Rocks reacting in the dark, gases moving slowly through frozen ground. But then Mars does something that does not look harmless at all. It breathes. Orbiters and rovers have caught it in the act. Thin, almost ghostly traces of methane appearing in the Martian atmosphere, rising in concentration for a season, then fading back into the background. On a planet where sunlight and chemical reactions should tear methane apart in a few hundred years or less, that is already disturbing. On Earth, methane is not an abstract concept. It seeps out of wetlands, bubbles from thawing permafrost, leaks from landfills, and pores from the digestive systems of livestock. It is what microbes in oxygen-poor environments exhale as waste. Only later do textbooks introduce the technical label, a potent greenhouse gas and a classic biosignature. But that is not the whole story. Methane can also emerge from geology alone. Water interacting with certain minerals in the crust can produce it without a single living cell involved. Serpentinization is the term scientists use for some of these reactions, and the result was clear on Earth long before anyone sent a probe to Mars. So when the Curiosity rover, sitting inside Gale Crater, began to detect tiny spikes of methane near the surface, the reaction was complicated. The readings rose during the Martian summer, dropped in winter, and occasionally surged in sudden plumes. The scary part is that seasonal breathing pattern looks uncomfortably familiar. Here is where things get uncomfortable. Instruments in orbit, like the ExoMars Trace Gas Orbiter, were designed specifically to hunt for gases like methane with extreme sensitivity. Yet for a while, they saw almost nothing, even when Curiosity reported a spike below. Two sets of eyes staring at the same world, disagreeing about whether the planet had just exhaled. The thing is, no clear source has been found. There are no active volcanoes belching gas into the sky. No confirmed subsurface reservoirs mapped out as obvious culprits. Just hints. A strange reading here, a brief plume there, numbers that rise and fall in patterns that do not line up neatly with dust storms, temperature, or known chemistry. Scientists have tried to imagine what would have happened if a similar signal appeared above an Earth desert instead. Would the first assumption be hidden microbes clustered in underground pockets of water? Or deep rock fractures where water and mineral surfaces quietly manufacture methane in the dark? On Mars, both explanations are disturbing. The incredible part was that each new measurement, each new mission, seemed to deepen the mystery instead of solving it. In other words, the planet is breathing something out, but no one can yet say from where or from what. So the question hangs over every new data set like a quiet threat. Is Mars slowly exhaling the last breath of a buried biosphere, clinging to existence beneath the dust? Or is this the signature of an alien kind of geology that does not care if it poisons future settlers? And if methane is only the first whisper, what else is this planet getting ready to release? That whisper of methane is not the only sound Mars is giving off, because in the last few years, microphones have finally started listening to this dead world. On the Perseverance rover and the earlier InSight lander, small, fragile microphones were exposed to an environment that is almost silent by design. They recorded thin, whispery winds slipping past metal, dust devils hissing over rock, and the faint creaks and groans of rover mechanisms straining in the cold. It does not sound like Earth, not even close. Mars has an atmosphere less than 1% as dense as the air at sea level here. That thin gas changes everything about sound. The result was audio that is lower in volume, shifted in pitch, and strangely muted, as if someone placed a hand over the planet's mouth. Gusts that would roar on Earth arrive there as distant, breathy sighs. Mechanical clicks smear into dull thuds. Between them sits a constant, almost suffocating quiet that feels less like peace and more like absence. Here's where things get uncomfortable. Those recordings are not just cool science extras. They are a preview of what a human standing on that surface would actually hear. Imagine it. The sky a dirty orange, the horizon sharp and empty in every direction. No birds, no insects, no distant traffic, no human voices. Only a faint, muffled wind somewhere far off, filtered through a helmet, and the soft ticking and humming of life support systems cycling behind the ears. The scary part is that the loudest sound in that landscape would be the technology keeping a person alive. In other words, the planet itself barely registers. For a while, scientists thought Mars might be completely quiet underground as well. Then InSight started listening in a different way. Instead of air vibrations, it heard the ground. The lander's seismometer picked up dozens of small quakes rippling through the crust. These Marsquakes were not like the catastrophic earthquakes seen on Earth, but their signatures were clear. Something inside this frozen world is still moving. The incredible part was what those vibrations implied. They hinted at a mantle and core that are still cooling and slowly shifting long after the surface oceans vanished and the air thinned. The planet is not alive in a biological sense, but it is not completely dead rock either. It is a body in a long, slow process of freezing solid. That is pretty disturbing when paired with the silence above. A world that looks still, sounds almost empty, yet quietly flexes and settles underneath. Engineers can model radiation levels, dust toxicity, and power requirements. The thing is, it is much harder to model what it will do to a human to stand in that kind of quiet for months at a time. Living on Mars affects the mind. Mars's day, a sol, is 24 hours and 39 minutes. Not 24 hours. Not close to Earth time. The 39-minute difference compounds. After a week, a colonist is 4.5 hours desynchronized from their sleep-wake cycle. After a month, they're operating on a day that's shifted by nearly half. Simulated Mars crews show consistent cognitive decline, sleep disorders, and mood disturbances. They make more mistakes. They react slower. Their judgment deteriorates. The Martian day doesn't align with human biology. A colonist can't simply adjust. They're permanently fighting their own circadian rhythm every single day for years. The isolation is bad enough, but isolation with your brain working against you, that's a different kind of hell. Because if the first impression of Mars is beauty through a telescope, the second, more honest impression might be this: a place that does not speak, does not welcome, and barely notices that anything is walking on it at all. And the longer missions last, the more that indifference starts to matter. That indifference is dangerous because from the right angle, Mars does not look hostile at all. Picture standing on a rocky ridge at Martian sunset, looking down into a canyon deeper than the Grand Canyon and stretching past the horizon. The sky overhead is fading from a pale butterscotch near the sun to a cold, deep blue straight up. The dust in the air turns the light soft, almost gentle. For a while, it could almost pass for peaceful. The thing is, that scene is already lethal. The air pressing against a helmet in that moment is almost entirely carbon dioxide, at less than 1% of Earth's sea level pressure. It is so thin that exposed saliva would start to boil, not because it is hot, but because there is almost no pressure to keep it liquid. The scary part is that this would happen long before anyone technically ran out of air. In other words, the romance of the view depends on forgetting what the atmosphere actually is. It is not just unbreathable, it is barely there. Any crack in a suit turns that beautiful canyon into a vacuum chamber. The result was the same in every simulation scientists have run: seconds of confusion, then unconsciousness, then nothing at all. But here is where things get uncomfortable. On Mars, the air itself is not the most disturbing threat. It is what rides on the air, what seeps through cells, and what never stops hitting from above. The invisible hazards turn that quiet landscape into a kind of slow, patient machine designed to take a human body apart. Dust is the first layer of that machine. Every rover image shows it: a fine reddish powder that coats everything and never really settles. Those grains are jagged, electrostatically clingy, and laced with perchlorates, chemicals that on Earth are used in rocket fuel and can disrupt thyroid function. Tracked into a habitat or ground into lungs, they do not kill quickly. They erode, irritate, and poison over months and years. Above that dust, the radiation never stops. With almost no magnetic field and only a thin atmosphere, Mars lets high-energy cosmic rays and solar particles slam into its surface day and night. We built instruments based on models. The models were wrong in ways we didn't expect. Ingenuity, the Mars helicopter, was rated for 5 flights. 5. Engineers gave it a 5-flight lifespan before mechanical failure or battery degradation would end its mission. It flew 72 times before finally failing, more than 14 times longer than predicted. This should be good news. Instead, it's unsettling. We don't understand why Ingenuity lasted so long. Either Mars is less harsh than we predicted, which contradicts all our other data, or something about Martian conditions is more unpredictable than we thought. If we can be wrong by a factor of 14 on a simple helicopter, what else are we wrong about? What else have we underestimated or overestimated? And then there is the mind. That same ridge at sunset, that same canyon, becomes a psychological trap when it is the only view for months. Isolation, unchanging horizons, the knowledge that a few millimeters of suit material stand between life and vacuum. It all adds up. What would have happened to judgment, to sleep, to basic motivation after enough Martian days in that environment? The next sections will move through this system of slow damage step by step. The radiation from above, the toxic dust underfoot, and the mental strain in between. Taken together, they show how Mars, for all its beauty, might be the closest thing in the solar system to a perfect place to die slowly. Radiation on Mars is not a dramatic flash or a single disaster. It is a quiet storm that never really ends. On Earth, a person stands under a shield. A global magnetic field deflects much of the charged particles from the sun, and a thick atmosphere soaks up the rest. On Mars, that shield is gone. The planet's magnetic field died billions of years ago, and its air is so thin it barely counts as protection at all. The result was simple and brutal. Mars was left almost naked in space. Every sunrise there, invisible particles begin pouring down on the surface. Some come from the sun during ordinary days. Others arrive in violent bursts during solar particle events. Beyond that, from far outside the solar system, there is a constant drizzle of galactic cosmic rays, high-energy bullets accelerated by ancient supernova. Rovers have actually measured this. Instruments on the Curiosity rover sat on the Martian surface and counted how much radiation hits the ground every day. It is not a vague threat. It is a number. In other words, living on Mars long-term would mean absorbing the equivalent of several chest X-rays every single day, stacked relentlessly on top of each other. The scary part is that radiation on Mars does not feel like anything. There is no burning sensation, no alarm going off in the air. The damage happens molecule by molecule, quietly shredding DNA, breaking chemical bonds, and leaving behind mutations for the body to clean up later, if it can. For a while, that might seem manageable. Humans in low Earth orbit already take higher doses than people on the ground and come back mostly fine. But the thing is, Mars settlers would not be up for 6 months or a year. They would be living under this storm for decades. Scientists have tried to estimate what would happen. The projections show significantly higher cancer rates, especially for blood cancers and solid tumors that might only appear many years later. There is evidence from animal studies that chronic radiation can damage the nervous system, changing memory, mood, and even basic cognition. Here is where things get uncomfortable. No one truly knows what continuous Mars-level radiation would do to embryos, pregnancies, or children growing up under that sky. Shielding is possible, but the physics is unforgiving. Protection requires mass, thick layers of water, heavy walls of regolith piled over habitats, or entire bases dug into the ground like modern cave systems. The incredible part was how quickly early concepts of glass domes and wide windows gave way to designs that look more like bunkers or underground parking garages. Simple surface living, with big views of the red horizon, becomes pretty disturbing once the numbers are added up. Every kilogram of shielding has to be mined, moved, or launched. Eventually, any long-term resident of Mars would be making a trade that is hard to ignore. Years of life expectancy exchanged for the privilege of standing on that world at all. And radiation is only the first layer. Under their boots, another threat waits in the dust itself, ready to follow settlers back inside and finish what the sky began. The dust looks harmless from orbit, a soft reddish haze rolling over empty plains. But down on the surface, it becomes something else entirely. Every step on Mars would kick up clouds of ultrafine particles. Not sand, not even talc, but grains ground down by billions of years of impact and frost. It behaves more like smoke than soil. It floats, it seeps, and the scary part is that it does not like to let go. Each particle tends to hold an electric charge. In other words, the planet's entire surface is wrapped in a thin layer of electrostatically clingy powder. It sticks to visors, to gloves to airlock walls. Apollo astronauts on the moon describe something similar, but Martian dust is even finer, and there is more of it. A lot more. For machines, this is a slow motion nightmare. Dust works its way into every seal, every hinge, every rotating joint. Over time, those particles become grinding paste, turning precision bearings into sandpaper. Filters clog, radiators get coated, solar panels darken. The result was already seen with robotic missions like Opportunity, where dust accumulation on panels helped end a nearly 15-year mission. For a while, engineers treated this as an engineering problem. Better seals, better filters, more robust joints. But here is where things get uncomfortable. The dust is not just abrasive, it is chemically disturbing. Martian soil contains perchlorates. These are reactive salts that on Earth are used in rocket fuel and explosives. At low levels, they interfere with the human thyroid, disrupting hormone production and metabolism. At higher exposures, they become directly toxic if inhaled or ingested. They had no idea at first just how pervasive these compounds might be across the Martian surface. Now imagine a typical day in a future habitat. A crew member returns from an EVA. The suit is coated in invisible, clingy dust, packed into fabric layers and mechanical joints. Even with careful brushing and air showers, some particles ride along, slipping past seals, hanging in the air like smoke. They settle on floors, on tools, on food prep surfaces. Every walk outside adds another thin layer of contamination. It does not look like poison. It looks like a faint red film on a tabletop. But over months and years, that film represents a constant low-level exposure to perchlorates and razor-edged mineral grains. The lungs would take the first hit. Fine dust can reach deep into the smallest airways, lodging there permanently. On Earth, long-term exposure to silica dust or asbestos scars lung tissue, leading to chronic inflammation, fibrosis, and cancer. Martian dust, with its sharp shapes and chemical reactivity, could be even worse. The incredible part was how quickly similar particles on Earth have ruined the health of miners and construction workers, even with regulations in place. Eventually, the body starts to lose the quiet war. Thyroid function drifts off normal. Breathing becomes harder. Micro tears in lung tissue give way to persistent coughing that never fully goes away. The thing is, this would not feel like a dramatic accident. It would feel like getting old too fast in a place that already wants every breath back. And outside the thin walls of that habitat, the planet keeps sifting more dust across the landscape, ready to slip into any crack that opens. The next threat waiting in that dust is not just chemical or mechanical. It is something stranger and possibly alive. The next incident is not an explosion or a crash. It is a morning. 5 years into the mission, the colonist wakes before the habitat lights come up, already aware of the dull ache in their knees and spine. Movement feels wrong. Not dramatic, not like an injury, more like a body that has aged decades in a place that has only seen a few Martian summers. They sit up slowly. The air is dry and metallic. A cough starts as a tickle and ends in a harsh, familiar fit that leaves a faint taste of dust. This has been happening for a while, often enough that it no longer feels like a symptom. It just feels like Mars. In the small medical bay, the routine begins. Bone density scan, blood draw, cognitive test on a flickering tablet that measures reaction time and memory. The results are not catastrophic. That is the scary part. Each number is only a little worse than last month, a little further from the body that first stepped off the lander. The scan shows thinning bones in the hips and spine, exactly where lower gravity does the most damage. Radiation badges, logged and archived, line up into a slow upward trend. Blood markers hint at cells that are dividing in ways they should not. No diagnosis yet, just a probability curve, bending. On the cognitive test, there is a half-second delay pressing the correct symbol, a missed pattern in a sequence that would have been effortless on Earth. Here is where things get uncomfortable. On a planet that demands constant vigilance, the mind responsible for staying alive is quietly, measurably slipping. The daily maintenance round feels almost comforting. The colonist pulls on a worn work harness and moves through the habitat like a caretaker in a fragile museum. Dust filters are pulled, tapped, vacuumed. Fine red powder drifts out, clinging to gloves and sleeves, carrying perchlorates that, in other words, can quietly attack the thyroid if they make it inside. Outside, in the thin afternoon light, the suit's outer layer shows new micro-abrasions that were not there last week. Tiny scratches from dust grains that behave like sand-blasting machines, driven by winds in an atmosphere less than 1% of Earth's pressure. Each mark is inspected, photographed, patched. Another minor radiation alert is logged from a solar flare that barely registered back home. The incredible part was how normal it all feels. This is just the job. The habitat hums. The machines work. The sky stays clear and dead and beautiful. But the colonist knows the math. Every extra sol adds to an invisible ledger of damage. Each sunrise over the same rusted horizon probably removes days, maybe years, from whatever life might still exist on Earth. It is pretty disturbing to realize that going outside to keep the base alive is also what is slowly killing the person maintaining it. Later, off duty, they stand at the small window in the airlock corridor. Outside is everything the posters promised. A vast, silent landscape, layered hills, a sky that glows but never truly turns blue. The question that will not go away is simple. What would have happened if this had been a one-way trip all along? They press a hand against us, the glass, feeling the faint chill. Somewhere far above, radiation continues to fall through the thin air. Somewhere far away, Earth's sky is bright and thick and noisy. The colonist stares into the Martian distance and wonders, not dramatically, but with a quiet, constant weight, whether those clouds will ever be seen again. Because on Mars, the most disturbing part is not how a mission ends. It is how long a person can keep going, knowing the planet is already writing their cause of death in slow motion. There is another problem waiting in that thin red sky. It does not arrive as an explosion or a storm. It arrives as a slow, quiet change inside the body. Mars pulls at everything with only about 38% of Earth's gravity. It is enough to stand, to walk, to jump, and feel strangely light. In other words, it feels safe. The scary part is that this almost normal pull may be exactly what makes it so dangerous over the long term. On the International Space Station, the rule is simple. Take away almost all gravity, and the human body starts to unravel. Muscles shrink, bones thin, blood redistributes, and the heart remodels itself for an easier job. The name for this is deconditioning, but that word sounds much gentler than what actually happens. Astronauts in microgravity can lose up to 1 to 2% of their bone mass per month, especially in the hips and spine. The result was entire parts of the skeleton behaving like those of elderly patients after only half a year in orbit. Intense exercise, restraints, and careful diets helped, but they did not erase the problem. They only slowed it down. Low gravity damages the skeleton. Bones weaken at roughly 1% per month, faster than weightlessness in orbit, which only causes 0.5% monthly loss. This is the cruel irony. Partial gravity provides enough stimulus to make your body think it's being used, but not enough load to maintain skeletal density. Your skeleton gets confused. It's not resting, it's not working, it's just slowly demineralizing. A colonist who arrives at Mars healthy becomes progressively fragile. After 3 years, their bones are 36% weaker. If they try to return to Earth's 1G gravity, their skeleton might not support their own weight. Partial gravity, like Mars offers, sits in a disturbing blind spot. It is not zero, so some of those effects will be reduced. But reduced by how much? Scientists have been asking that question for a while, and the truth is that no one has lived in one-third gravity long enough to know. Here is where things get uncomfortable. If 38% is not enough to fully maintain muscle and bone, then every Martian year becomes a small step away from Earth. Imagine a colonist returning after a decade on Mars. The trip home ends, the capsule lands, the hatch opens. Earth's full gravity hits like a weight that never existed on Mars. Standing up could feel like wearing a concrete suit. Heart rate spikes. Blood pressure crashes. Bones that adapted to a gentler pull are suddenly asked to carry almost 3 times the load. What would have happened inside that body over all those years? Subtle bone loss that never quite stopped. Leg muscles and back muscles tuned for lighter work. A heart that learned it did not need to fight as hard against gravity. Back on Earth, that same heart might struggle just to push blood to the brain without fainting. The incredible part was not how fast astronauts recovered from short missions. It was how even they needed weeks or months of rehabilitation just to walk and live normally again. Now extend that to settlers who have children on Mars. A child born and raised in one-third gravity might grow taller, with different posture, different bone density, different cardiovascular limits. For that person, Earth's gravity would not just feel heavy. It could be medically intolerable. Stepping onto the home planet of their species might be as dangerous as stepping onto a high-gravity exoplanet. In that scenario, Mars stops being a destination and becomes an evolutionary fork. Generations adapt to the red planet's pull until returning to Earth is not just difficult, but physically impossible. The trap is not a malfunctioning rocket or a failed launch window. It is biology, quietly rewriting what a human body can survive. And if gravity alone can do that, what else on Mars is already pushing human evolution in directions that cannot be reversed? If gravity can quietly turn future Martians into a different kind of human, isolation can do something just as permanent, but from the inside out. On Mars, the prison walls are not metal bars. They are distance, silence, and a planet-wide desert that almost never changes. Outside the habitat, the landscape is nearly featureless, endless red and brown, broken only by rocks and dust-softened craters. The sky stays a thin, pale haze, sometimes tinted but rarely dramatic. There are no clouds rolling in, no rain, no snowstorms with familiar sounds, no trees moving in the wind. In other words, almost nothing moves unless a machine makes it move. Inside, the contrast is not comforting. There is the constant mechanical hum of pumps, fans, air recyclers, and life support systems. A low, ever-present vibration through the walls and floors. At first, it would be reassuring. Eventually, it becomes a reminder that if that sound ever stops, so does everything else. The scary part is that silence on Mars is not peaceful. It is an emergency. Communication with Earth does not feel like a conversation. At the speed of light, the delay can stretch beyond 20 minutes each way. A simple question can take nearly an hour to fully answer. Jokes do not land. Reassurance arrives long after the moment of fear has passed. For a while, crews might try to in real time anyway. Then the reality sets in. Every exchange becomes slow, asynchronous, more like sending messages into the past than talking to another person. Talking to Mars is difficult. The signal takes 3 to 22 minutes to reach Mars, depending on orbital position, meaning real-time conversation is impossible. But there's another problem. Mars's ionosphere fluctuates wildly. Radio communication windows shift 20 to 30 minutes daily. Solar flares can block transmissions entirely for 6+ hours. A colonist trying to call Earth during an emergency might find the ionosphere opaque. They can't schedule a conversation with Earth the way astronauts on the ISS can. They're dependent on communication windows that shift daily, that can close without warning, that can remain closed during a crisis. A colonist isn't isolated by distance. They're isolated by physics, by the Martian atmosphere, by the solar wind, by the ionosphere. They're alone, but not by choice. By the laws of nature. The habitat itself is not large. Early Martian bases will be sealed shells, pressurized tunnels, or buried modules just big enough to stay efficient. The result was predicted long before anyone steps onto Mars. Small social circles, the same faces every day, nowhere else to go. Stepping outside is possible only inside a suit, tethered to life support, with death a few millimeters away at all times. Here is where things get uncomfortable. The entire planet is technically open, but functionally off limits. Scientists already have a preview of what that does to the human mind. Antarctic winter crews live through months of darkness, confinement, and isolation, and even there, with breathable air and an escape route, rates of depression, sleep disruption, and conflict rise. Long-duration isolation experiments in sealed habitats on Earth show similar patterns. Mood swings, strained relationships, and a growing sense that the outside world is unreal. And those are the training runs, with rescue always possible. On Mars, there is no quick evacuation, no helicopter out, no hospital a few hours away. The incredible part was how often analog crews reported feeling watched by the environment itself, as if the landscape were pressing in. On a planet-wide desert, that pressure could be constant. The thing is, the first permanent Martian settlements might not feel like heroic frontier towns at all. They may feel more like beautifully furnished prisons with better views. And if the walls start closing in on the mind, what does that do to the decisions a trapped colony makes next? There's a detail that almost never appears in glossy Mars concept art. Somewhere in those pressurized corridors and domes, sooner or later, there will be a body. In any serious, long-term settlement, statistics stop being abstract. Over hundreds of EVAs, thousands of maintenance tasks, and years of exposure to a hostile environment, accidents and medical emergencies are not hypothetical. They are guaranteed. The scary part is that on Mars, even a minor failure can escalate into something that looks less like an accident and more like a slow-motion execution. Imagine an EVA on the edge of a dust storm. Visibility drops. A sharp rock punches through a boot or a knee joint. It is just a puncture. On Earth, it might mean stitches. On Mars, it means a suit breach, rapid decompression, and a race against physics. The result was calculated long before anyone stepped outside. With that pressure difference, there are only seconds of useful consciousness. Inside the habitat, the risks change shape, but never disappear. A micrometeoroid hits a thin section of the shell. A valve sticks. A door cycles open at the wrong time. Decompression in a module would not look dramatic from the outside. Inside, it would feel like the air being stolen from lungs in silence. For a while, everyone would wonder what would have happened if one checklist had been followed slightly differently. Then there is the slower threat: a sudden stroke, a burst appendix, a cancer that radiation quietly accelerated over years. On Earth, an ICU might be minutes away. On Mars, advanced care is a planet away. Here's where things get uncomfortable. Medical triage in a place like that is not just about saving a life. It is about deciding how much of the colony's limited oxygen, drugs, and power are worth spending on a case that may already be lost. And when that first person dies, another disturbing question appears. What happens to the body on a frozen desert world that never asked for one? Burial in Martian soil sounds poetic, but the regolith is loaded with perchlorates and reactive chemistry. A grave becomes a chemical experiment. Cremation demands oxygen and fuel that settlements can barely spare. Storing bodies in a cold room turns the habitat into a quiet morgue. In other words, even in death, the dead compete with the living for resources. Eventually, someone will suggest a Martian cemetery, rows of markers half buried in dust, on a planet that already looks like a graveyard of failed probes. The incredible part was that engineers once joked about the great galactic ghoul eating spacecraft. A real colony might discover that the planet does not need to sabotage machines. It only has to wait. But the first death might not come from equipment at all. Isolation, confinement, and the pressure of knowing there is no way home can twist a mind. Psychologists already worry about depression and psychosis on long missions. The scary part is that a suicide in a closed system is not just a tragedy. It is a contamination event, a logistical crisis, and a psychological shockwave moving through a tiny, trapped population. After that, how does a settlement even talk about risk or consent or staying versus leaving when leaving is impossible? When the first human dies on Mars, will it be remembered as a tragic milestone on the way to a multiplanetary species, or as the quiet moment a small group of people realized they were less like explorers and more like residents of a place they could never truly escape? And if that realization comes too late, what decisions does a cornered civilization make next? That realization might not be the end of the story. It might only be the beginning of a different kind of presence on Mars, the kind that can no longer answer back. From orbit, the first clues are visible: a scatter of straight lines on an otherwise chaotic landscape, glints of metal half buried in rust-red dunes, a collapsed dome frozen mid-implosion. In other words, the planet looks less like a frontier and more like a museum that never hired a curator. On Earth, plastic decays, metal rots, and microbes patiently take everything apart. On Mars, there is almost nothing alive to do that work. No rain, no running water, just cold, dry, airless silence. The result was that even a simple spanner dropped in the dust might survive longer than many species back home. Here is where things get uncomfortable. Inside a cracked habitat, frozen airlocks still hold pressure in a few sealed compartments. There are beds, personal tablets, half-finished experiments. There might even be mummified remains, skin and fabric shrunken together, preserved not by reverence, but by -80 degrees and a total absence of decay. The archaeologist walks through a greenhouse filled with desiccated roots, finds a 3D printer loaded with half-used regolith feedstock, sees thick radiation shielding over sleeping quarters, but thin protection over communal areas. What conclusions come next? Maybe the record suggests a species obsessed with power generation, life support, and constant communication with a distant blue world. Maybe data logs show that for a while, more bandwidth was devoted to entertainment than to safety drills. That is pretty disturbing when the entire sky is lethal. The incredible part was never the technology itself, but what it says about priorities. Massive reactors, delicate water recyclers, elaborate rovers, all built to keep fragile bodies alive in a place that clearly did not want them there. What would have happened, the archaeologist wonders, if that ingenuity had been aimed at leaving fewer scars instead of more monuments? Because Mars keeps records: failed landers, abandoned habitats. Even the first human grave dug into permafrost will remain, long after oceans on Earth have shifted shorelines beyond recognition. And in the geological timescale, that means every choice made on this planet is less an experiment and more an inscription, waiting for whatever comes next to read it. Those inscriptions are not just metal and bone. Some of them are made of light. Because every so often, Mars does something that should not happen on a dead world. A single frame, a strange glow on the horizon, a measurement that refuses to behave. And for a while, even the most cautious scientists have to admit they are looking at something that does not fit. The thing is, the expected dangers on Mars are already disturbing enough. Radiation, toxic dust, lethal cold. All of that can be modeled, simulated, planned around. But then there are the moments when the cameras blink, the sensors spike, and the planet briefly looks less like a predictable desert and more like a stage where something else is moving just off screen. One of the most unsettling examples came from the Curiosity rover in 2014. In a sequence of images, a bright, thin light appears above the distant ridgeline. It is there in one frame, gone in the next. No nearby dust devil, no obvious reflection, just a needle of light reaching upward from the Martian surface. Within hours, speculation exploded. Was it a cosmic ray hitting the detector? A glitch in the electronics? Sunlight bouncing off a rock at exactly the right angle? Or was it something physically glowing on the ground, however briefly? For a while, no one could say with complete certainty, and the scary part is that the data record is only those frozen frames. There is no second angle, no follow-up. Other rovers have seen their own flashes and odd glints near the horizon. Sometimes the explanation eventually settles on sensor noise or high-energy particles striking the camera. In other words, the light never existed on Mars at all, only inside the hardware. But here is where things get uncomfortable. Not every anomaly collapses that neatly under analysis, and not every strange signal can be written off as a bad pixel. The rocks themselves add another layer of unease. Again and again, orbital images and rover panoramas reveal shapes that look eerily familiar, something that resembles a doorway cut into a cliff, a boulder that looks like a statue, a slab that could be a toppled pillar. Pattern-seeking brains lock onto these forms instantly. What would have happened if the first blurry face in Cydonia had appeared in the age of social media rather than the Viking missions of the 1970s? The incredible part was how often later, higher resolution passes erased those illusions completely. The doorway becomes a small fracture. The statue collapses into random angles. The result was a reminder that Mars is a master of pareidolia, generating accidental structures out of wind, sand, and shadow. But not everything has been so easy to dismiss. methane spikes that appear and vanish, pressure readings that hint at strange near surface processes, odd acoustic signatures in the thin air. This next part is a tour through those Martian ghost stories where camera glitches end and the genuinely puzzling data begins. The first time it happened, it looked almost like a heartbeat in the data, a tiny pulse of gas in an atmosphere that was supposed to be dead and predictable. In 2013, NASA's Curiosity rover sitting inside Gale Crater detected a small but measurable whiff of methane, not a steady background level. A spike. It rose above the instrument's baseline, lingered for a while, then faded back into almost nothing. On Earth, methane in the air is often tied to life. Microbes, wetlands, even livestock. On Mars, that same molecule suddenly became a kind of accusation. Oh, something was making it or releasing it in a place that was supposed to be geologically quiet and biologically empty. Curiosity kept watching. Over multiple Martian years, it saw a pattern. Methane levels near the surface seemed to rise and fall with the seasons, peaking in the warmer months and dipping in the cold. Then, every so often, there were sudden localized bursts where the concentration briefly jumped several times higher than usual before collapsing again. The incredible part was that orbiters flying overhead did not always agree. ESA's ExoMars Trace, gas orbiter designed specifically to sniff out trace like methane from above, often reported nothing at all over Gale Crater, even when Curiosity was measuring a spike right under that same patch of sky. In other words, one set of instruments said the air was breathing, while another said it was almost perfectly still. The lighter elements escaped first, because Mars's escape velocity is only 5.03 kilometers per second, half of Earth's 11.2 kilometers per second. Hydrogen and helium didn't stand a chance. They fled preferentially in a process called fractionation. The heavier gases, nitrogen, argon, CO2, stayed behind longer, creating a temporary atmosphere that was denser than the current one, but less breathable. For a brief window in Martian history, the planet might have looked almost habitable. Then the heavier gases started escaping too. The process was asymptotic. Each loss made escape easier for what remained, because less atmospheric pressure means less drag on escaping molecules. The thing is, there are ways to make methane without life. Water interacting with certain minerals deep underground can trigger chemical reactions called serpentinization, generating hydrogen that then combines with carbon to form methane. Ancient pockets of gas could be trapped in the crust, sealed for millions of years, and released through tiny fractures as the ground flexes with temperature changes. Clathrates, icy cages that can lock away gas, might destabilize and burp their contents when the subsurface warms. Those explanations are comforting because they are non-biological. But here is where things get uncomfortable. None of them fully explain why the methane seems to appear in sharp, localized plumes and then vanish faster than simple chemistry or winds should allow. Above the surface, the story gets even stranger. In 2012 and 2015, observers reported enormous towering plumes or localized clouds in Mars's upper atmosphere, reaching altitudes of 200 to 250 kilometers. They appeared over the limb of the planet, bright enough to be tracked from Earth-based telescopes, then disappeared within days. For a while, scientists argued over whether they were auroral emissions, dust, ice, or an instrumental illusion. The result was no consensus, just another disturbing question mark. The scary part is that the instruments themselves sometimes behave like unreliable witnesses. One orbiter sees a cloud, another looking at the same region sees nothing. Curiosity smells methane. A high-precision spectrometer overhead reports a hard vacuum of silence. Mars was supposed to be simple: thin air, weak weather, a fossilized sky. Instead, it keeps hinting at moving air, flickering plumes, and gases that do not act the way they should. Its atmosphere is more dynamic and more poorly understood than mission planners like to admit, leaving open not just the possibility of hidden chemistry, but the unsettling idea that something important is happening there that no one yet understands. Mars keeps doing something else. It keeps showing shapes that look disturbingly familiar. The most famous case didn't start with a rover, but with a flyby in 1976. The Viking 1 orbiter sent back a grainy black and white image of a plateau in the Cydonia region. In that low resolution, with the sun at just the right angle, a mesa suddenly looked like a colossal human face staring up from the dust. It had eyes, a nose, even what looked like a mouth and a brow. For a while, entire books and documentaries insisted this was proof of an ancient civilization. The scary part is, scientists also took it seriously enough to check, not because they believed in a carved monument, but because if it was artificial, everything about Mars would change overnight. Eventually, higher resolution cameras arrived. Mars Global Surveyor and later Mars Reconnaissance. Orbiter passed over the same coordinates. The face dissolved into what it really was: a lumpy, eroded hill with ridges and shadows doing all the work. No eyes, no mouth, just rock. The result was supposed to be reassuring. In other words, the planet was behaving like a planet, but something about that first image still lingers because the human brain is wired to see patterns, and especially faces, a phenomenon called pareidolia. It's an ancient survival system. Spotting a predator's face in the dark a fraction of a second faster could mean the difference between life and death. On Mars, that same wiring becomes a trap. Low light, long shadows, dust-softened edges, and compressed images from millions of kilometers away all combine into an almost perfect illusion machine. A random boulder becomes a skull. A cluster of rocks becomes a ruined doorway. A trick of contrast turns a slope into what looks like a statue watching the horizon. More recent missions have only amplified this effect. One set of images from the south polar regions showed dark, branching structures that look like huge spiders crawling across the ice. Another frame captured a rock formation that at first glance resembled a crab clinging to the wall of a Martian cliff. There have been fossil fish, helmets, even something that looked disturbingly like a humanoid figure frozen mid-step. Here is where things get uncomfortable. Many of these shapes have very real, very non-biological explanations. The spiders are created when carbon dioxide ice builds up in winter, then explosively vents gas in spring, carving radial channels in the dust. The crab is just a collection of rocks highlighted by contrast stretching. Wind abrasion, thermal cracking, landslides, and ancient floods all sculpt the surface into bizarre, misleading forms. The incredible part was how fast each of these images spread before the explanations caught up. For a few hours or a few days, the idea that something alive might be there felt plausible again. And the scary part is, even after the geology is understood, some pictures still trigger a quiet, instinctive reaction, a sense that something with eyes is hidden in the frame, looking back across the gulf of space. The question that hangs over the next images is simple. What happens when something shows up that stubbornly refuses to be explained away as rock and shadow? The next disturbing detail is not in the images at all. It is in the silence between them. Most of what is known about Mars does not arrive as a steady stream. It comes in bursts. Short communication windows when an orbiter swings over the horizon, lines up its antenna, and for a few minutes the planet speaks. Then the link cuts, the ground track moves on, and an entire world goes quiet again. During those long gaps, the rovers and landers keep working. They drive, drill, listen, and log, their computers filling with numbers and compressed thumbnails that no one on Earth will see for hours, sometimes for days. In other words, the machines are awake on a dead planet, but their signals are trapped in a kind of delayed echo. Here is where things get uncomfortable. Imagine the landscape in those missing hours. Thin winds dragging dust across old wheel tracks. A dust devil twisting suddenly out of nowhere, crossing the path of a rover that is turned the wrong way to record it. A small slide on a crater wall, erasing a set of ancient layers before any camera is pointed in that direction. The incredible part was how much has already been missed in plain sight. Opportunity once photographed its own tracks being partially wiped by passing whirlwinds. Curiosity has seen fresh scars on slopes that were intact in earlier images. The result was a quiet admission from scientists that even in the tiny regions that are monitored, Mars is not completely still. It moves when no one is listening. The scary part is what happens everywhere else. There's no continuous global surveillance, no unblinking eye watching every valley and canyon. Just snapshots, a mosaic of brief, carefully scheduled looks stitched together into a story that might leave out the most important scenes. For a while, some teams hoped orbiters could fill that gap. High-resolution cameras pass over the same spots again and again, but those passes are days, weeks, or months apart. A transient light, a brief plume, a local storm that rises and collapses in a siesta's afternoon would appear as nothing more than a before and after difference, or not at all. The thing is, Mars already hints at rare events that do not fit neatly into a static picture. Seasonal methane spikes that rise and fall with no confirmed source. Mysterious lights in single frames that might be cosmic rays or might be something at the horizon that flashed and vanished between exposures. What would have happened if a camera had been watching a few seconds earlier or a few meters to the side? So every time a downlink ends and the carrier tone fades, a question hangs over the empty spectrum. In the next unseen hour on Mars, is nothing happening? Or is something happening that no instrument is pointed at and no one will ever know existed? For a while, the worst case scenario was that something was happening on Mars that no one would ever see. The scary part is that the next scenario is much worse. Something might happen there because humanity decides to make it happen. Terraforming Mars. In other words, deliberately trying to turn a frozen, thin-air desert into a world that feels more like Earth, even if it takes centuries. The basic idea sounds simple. Warm the planet, thicken the atmosphere, and let liquid water return to the surface. The result was supposed to be blue skies over red rock, lakes in old impact basins, maybe even forests where there are only dunes today. To get there, the proposals become increasingly aggressive. One plan suggests releasing enormous amounts of greenhouse gases, far beyond anything Mars can produce naturally. These would trap heat, melt buried ice, and start a feedback loop of warming. Another idea is to import volatiles, the substances that can become gas or liquid, by redirecting icy comets and asteroids to slam into the planet. The impacts would vaporize water and carbon dioxide, seeding a thicker atmosphere in a series of controlled, planet-scale explosions. Others imagine orbital mirrors, gigantic reflective sheets stationed in space, focusing sunlight onto the poles. It would be a permanent artificial sunrise, slowly turning layered ice into vapor. For scientists running the numbers, the incredible part was that, on paper, some of this might actually work over long timescales. Here is where things get uncomfortable. All of these schemes assume that Mars is effectively dead, a place with interesting chemistry, but no native biosphere left to harm. But the thing is, the evidence is not that clear. Seasonal methane spikes keep appearing in the thin air, rising and falling in ways that are still not fully explained. Certain minerals form more easily in the presence of liquid water and potentially biology. Deep underground, where radiation is weaker and temperatures are less brutal, there might be isolated pockets of brine or rock fractures that have been sealed for billions of years. Radiation on Mars is severe. We're talking 200 to 300 millisieverts annually at the surface, equivalent to roughly 40 full-body CT scans per year, compressed into the Martian sky. But that's the baseline. A single solar particle event, which happens unpredictably, can deliver 1 sievert in hours. A sievert is significant. The LD50, dose that kills 50% of exposed subjects, is 6 to 8 sieverts acute exposure. One bad solar storm, 1 hour outside shielding, and a colonist is playing Russian roulette with their bone marrow. If even a simple microbial ecosystem is hiding there, clinging to the last habitable niches, then the ethical question becomes disturbing very quickly. Would large-scale terraforming be saving a dead world or killing a living one that just does not look alive from orbit? Once the atmosphere is thickened, once the temperature is pushed upward, and the chemistry of the soil is altered, there is no easy way back. On human timescales, these changes are effectively irreversible. There is no switch to restore the old climate if something unexpected starts to die or starts to spread. They had no idea, in the early science fiction stories, what it would mean to overwrite an entire planet's history with a new, engineered one. Now every serious proposal carries the same quiet question. What would have happened on Mars if nothing had been changed? The next step is even more disturbing, because before any global transformation, there is the smaller personal version: sealed colonies, struggling ecosystems and domes, and the reality of what it would take for human bodies to survive on a planet that does not want them there. Terraforming Mars sounds clean and cinematic. One day it is red and dead, the next it is blue and alive. The scary part is that the real physics behind that fantasy is much closer to a slow motion disaster than a miracle switch. Right now, Mars is missing almost everything that makes liquid water possible on its surface. The air is thin, less than 1% of Earth's pressure at sea level. The cold is brutal, with average temperatures far below freezing. In other words, even if ice is melted, it does not stay as water for long. It boils away into the thin air or freezes again. So the first idea sounds simple: thicken the atmosphere, trap more heat, use greenhouse gases to warm the planet until ice turns to water and seas begin to form. For a while, scientists hoped the raw material was already there, locked in polar caps and buried in the soil. Here is where things get uncomfortable. Orbiter data and lander measurements suggest that the total amount of carbon dioxide available on Mars is far lower than early dreams assumed. There is CO2 in the polar caps, frozen into layered ice. There is more trapped in dust and rock as carbonates. But when the numbers are added up, the result was disturbing. Even if almost all of it is released, the pressure might still be only a small fraction of Earth's. The dust itself is hostile, not just abrasive. Toxic. The Martian regolith is perchlorate rich, 0.5 to 1% by weight of a compound called perchlorate, an oxidizer used in rocket fuel. Breathe it in, and it damages cell membranes. Accumulate it in your body, and it interferes with thyroid function, which controls metabolism, mood, and cognitive function. A colonist isn't just dealing with radiation and low gravity. They're breathing in rocket fuel, slowly, for months or years. We don't fully understand the long-term effects because we've never exposed humans to Martian dust for extended periods. Equipment degrades faster than expected. Seals fail. Instruments corrode. The Martian dust has a Mohs hardness of 6 to 7, similar to quartz. That means it's abrasive enough to scratch and pit spacecraft equipment over weeks, not years. Imagine sandpaper that never stops working. A colonist's suit gets pitted. Their helmet scratches. The fine dust works into mechanisms, grinds against joints, and slowly transforms precision tools into grinding stones. The incredible part was how big the gap turned out to be. To reach something even marginally comfortable, proposals started to include manufacturing powerful synthetic greenhouse gases on an industrial scale, or importing ammonia-rich ice from the outer solar system. That sounds abstract until the scale is compared. It would mean redirecting icy bodies tens of kilometers wide, again and again, just to nudge the global temperature a little. The energy required is staggering. Warming an entire planet is not like heating a house. It is closer to running every power plant on Earth non-stop for centuries and still barely moving the needle. Realistic models talk in timelines of centuries to millennia, not decades. During that entire time, the planet would be in a shifting, unstable, in-between state. What would have happened if a single miscalculation pushed it the wrong way? Unintended consequences start to multiply. Rapidly warming the poles could destabilize buried ice, causing landslides and outgassing events. A thicker, dustier atmosphere could turn the already dangerous Martian dust into a planet-wide weapon, with more frequent global dust storms that block sunlight for months. A climate tuned to be barely habitable might swing wildly with each storm season, freezing and thawing in cycles that destroy infrastructure. The thing is, there is no backup copy of Mars. Terraforming is not a controlled lab experiment. It is a one-way planetary gamble. Any mistake would be written across an entire world. Eventually, some plans even imagine altering Mars's orbit or importing entire moons for extra mass. At that point, the question changes, not just whether Mars can be remade, but whether a civilization that struggles to manage one planet should be trusted to rewrite another. For a while, that sounded like pure science fiction. Rewrite a planet, move a moon, change an orbit. But there is a quieter question sitting underneath all of that power. If Mars can be changed, who has the right to change it? Modern space law tried to answer this long before serious Mars plans existed. In 1967, at the height of the Cold War, nations signed the Outer Space Treaty. It said that no country can claim sovereignty over the Moon, Mars, or anything else in space. In other words, no flags turning planets into territory. Getting to Mars is hard. Many missions fail. We've only succeeded a handful of times. The problem is atmospheric. Mars's atmosphere is too thin for parachutes alone. A parachute is useless when there's almost no air resistance. But the atmosphere is too thick to ignore. A spacecraft entering at orbital velocity experiences heating and drag that can destroy it. There's a Goldilocks zone of entry conditions that's brutally narrow, too shallow, and you skip off the atmosphere like a stone on water. Too steep and you burn up. Too fast and you're destroyed. Too slow and you're not in orbit anymore. Dozens of landers have crashed trying to navigate this corridor. The Mars rover graveyard includes Spirit, buried in dust, Opportunity, dust storm, and Beagle 2, parachute failure. But there are others, unnamed failures, missions we barely remember because they failed before they could succeed. Each failure teaches us something, but we keep failing because the corridor is that narrow. The scary part is what it did not say. It left a disturbing gap around private companies, resource extraction, and long-term settlements. Later agreements and national laws began to treat space resources as things that can be mined and owned, even if the world beneath them can never officially belong to anyone. The result was a legal landscape that looks clear on paper and very murky in practice. Into that murk, competing visions of Mars are already forming. Some scientists argue it should become a planetary park, a protected scientific preserve where minimal contamination is the rule. Others promote Mars as a backup world, a place to reboot civilization after an Earth catastrophe. And then there is the resource frontier model, where corporations and nations see frozen water, metals, and vast land as assets waiting to be exploited. Here is where things get uncomfortable. Those visions cannot all exist on the same planet at the same time. There is an even deeper question. What if Mars is not entirely dead? If microbial life is discovered under the ice or deep in the crust, that would mean an independent ecosystem, however small, has managed to survive for billions of years. On Earth, entire conservation efforts are built around protecting complex animals and forests. On Mars, the only native inhabitants might be bacteria. Does a Martian microbial ecosystem have moral standing against human plans? If terraforming would drown or poison that biology, is that an acceptable sacrifice or an extinction event carried out on another world? The incredible part was that, for decades, mission planners operated under the assumption that Mars was lifeless. They had no idea whether the first human footprints might also be the first invasive species. Then there are the future Martians who are not microbes. Children born in lower gravity, under domes and rock, adapted to a thinner atmosphere and different radiation levels. Who decides their laws and citizenship? Can Earth governments claim them? Can corporate charters bind them? Could they be compelled to stay on a world their bodies are shaped for, or forced to return to one that might slowly kill them? The thing is, Mars is becoming a test of whether humanity has learned anything from centuries of colonization, extraction, and broken promises on Earth, or whether the same patterns will simply be replayed on a colder stage. And somewhere in that tension, another possibility is waiting, one that does not fit neatly into any treaty or corporate plan, and it might already be hiding in the thin Martian air. So imagine the tension in that thin air suddenly becoming literal, not in a lab, not in a control room on Earth, but under a pressure dome on Mars, where the first courtroom in human history stands on a planet that never consented to any of this. The room is small. Transparent panels show a faint red horizon beyond the habitat, dust drifting past like slow smoke. Inside, there is a raised bench, a flag, rows of molded plastic seats. It looks disturbingly normal, like a district court transplanted into a survival bunker. At the center is the case that everyone in the colony has been whispering about for a while. A private consortium is accused of drilling into a subsurface ice deposit and contaminating it, not just with machinery and waste heat, but with Earth microbes, leaked from imperfect seals and rushed procedures. That ice was not just water. Seismic data and chemical readings suggested it might have sheltered native Martian microbes deep below the radiation baked surface. In other words, one of the last places on this world where something truly alien could still be hiding. On one side, company lawyers in immaculate suits, printed on site but cut to match Earth fashion. They talk about survival metrics, cargo manifests, shareholder obligations. The colony needed water. The launch windows were fixed. Delays would have meant empty tanks, failing life support, and people dying in a place already famous as a graveyard of failed missions. On the other side, scientists who have spent entire careers staring at blurry images of dried riverbeds and ancient shorelines. They remind the court that Mars once had oceans, clouds, even a climate that did not instantly kill unprotected humans. The result was a world that collapsed, lost its magnetic field, and became a frozen desert. The scary part is no one is fully sure why. Here is where things get uncomfortable. The scientists argue that the ice deposit might have been the last untouched biological archive on the planet. If anything lived there, it could have held answers about what would have happened to early life under a dying sky. Instead, drill mud, lubricants, and bacterial spores may have flooded the cavity. The executives respond with something colder. They point out that investors back on Earth did not fund a museum. They funded a foothold. Under the contracts that built this dome, resource extraction is not optional. It is mandatory. Without it, the colony folds, the habitat depressurizes, and Mars wins by default. The incredible part was how ordinary the arguments sound. Case numbers, exhibits, procedural objections, all the ritual of law performed under a sky that has erased entire atmospheres before. The thing is, the planet does not care who is technically correct. For a moment, the judge looks past the glass, toward the dust and the dead volcanoes. Then the gavel falls, and a precedent is born on a world that might still be hiding its own precedents in buried ice. And if this is how the first dispute over a single ice pocket looks, what happens when the argument shifts to something much larger than a courtroom and much older than any human contract? The argument shifts to the planet itself. Because before Mars became a legal battleground and a mining target, it was something else. It was a world that, for a while, did not look dead at all. Billions of years ago, early Mars and early Earth were disturbingly similar. Both had thicker atmospheres. Both were wrapped in volcanic activity. Both showed signs of rivers and lakes running openly across the surface. In other words, Mars was not always the rusted vacuum seen through a telescope today. Orbital images reveal dried-up deltas, winding valleys, and shorelines that trace the outlines of what could have been entire oceans. Minerals on the ground only form in long-standing water. The result was a picture that made scientists pause. This place once had clouds, rain, maybe even coastlines and storms. Then something happened. Mars did not just cool off or dry out. Its entire climate system collapsed. As the small planet's core cooled, its global magnetic field faded. Without that invisible shield, the solar wind had direct access to the atmosphere. Over millions of years, charged particles from the sun stripped it away, molecule by molecule, until most of the air and most of the surface water were simply gone. The scary part is that this was not a single impact, not a one-day catastrophe. It was a slow, grinding removal of habitability. A transformation from potentially blue to permanently red. Here is where things get uncomfortable. Earth is not about to turn into Mars next year, or even in the next 1,000 years. The planets are different sizes, different distances from the sun, with different internal heat. But the thing is, Earth's climate stability also depends on protective systems that can be pushed, stressed, and damaged. On Earth, that protection looks like a thick atmosphere, an active magnetic field, and a delicate balance of greenhouse gases. Human activity is now testing those balances in ways that no previous civilization has ever attempted. Massive carbon releases, ozone depletion, orbital debris, even the possibility of future geoengineering schemes all add stress to a system that evolved under much quieter conditions. Mars, frozen and thin-aired, is what a planet looks like when those protections fail and nothing stops the trend. Studying it is not just escapism or a backup plan. It is a forensic investigation of a climate crime scene, preserved in rock and ice. The incredible part was that when data from missions like MAVEN started to quantify how fast Mars lost its atmosphere, it became clear this was not a minor leak. It was an evacuation. What would have happened if Mars had stayed shielded just a little longer? Would that ocean have lasted, and would something have evolved beneath its waves? For scientists watching Earth's graphs bend and spike, Mars is starting to look less like a distant curiosity and more like a time lapse of a worst-case scenario, a preview of what a world becomes when the feedbacks that keep it stable are broken and nothing resets them. The disturbing question is not whether Mars is our destiny. It is whether the red planet is quietly showing what is physically possible when a world's safeguards are removed. And if Mars is the afterimage, the next step is to ask what the transition looks like in real time, while a planet is still fighting back. The transition already happened on Mars. The disturbing part is how quietly it unfolded. For a while, the planet looked stable from the outside, a small, colder cousin of Earth, wrapped in a modest atmosphere, with liquid water moving across its surface. Then something shifted deep inside. The core cooled, the internal dynamo slowed, and the global magnetic field that once wrapped Mars in an invisible shield began to flicker and fail. The result was not dramatic in the way disaster movies imagine. There was no single impact, no instant firestorm. Instead, charged particles from the sun found an exposed target. They began stripping away the upper atmosphere, atom by atom. In other words, a subtle change in internal physics translated into a surface-wide transformation that no organism on the ground could have stopped. The scary part is that this loss did not just thin the air. It rewired the climate. With less atmosphere, Mars lost much of its greenhouse effect. Temperatures dropped. As the planet cooled, gases that had once stayed comfortably in the air began to freeze out onto the surface and the poles. That meant even less atmosphere, even weaker warming, even more freezing. Here is where things get uncomfortable. This is a feedback loop. Less air leads to more cooling. More cooling locks away more gas as ice, which leads to even less air. Eventually, the system runs away from its original state. What would have happened if the magnetic field had held a little longer or the atmosphere had been a little thicker is now an unanswerable question. On Earth, the details are different, but the logic is disturbingly familiar. As polar ice melts, bright reflective surfaces shrink, exposing darker ocean that absorbs more sunlight and heat. Warming accelerates. As permafrost thaws, it releases methane and carbon dioxide once trapped in frozen ground. Those gases amplify the greenhouse effect, which melts more permafrost. Even the oceans, which feel permanent, are part of this fragile machinery. Changes in temperature and freshwater input can disrupt major circulation patterns that move heat around the globe. The thing is, once those patterns shift beyond certain thresholds, they may not simply snap back when conditions change again. On Mars, the runaway direction was toward cold, thin, and dead. On Earth, many of the feared runaways point toward hot, wet in some regions, bone dry in others, and violently unstable. The mechanisms are not identical, but the principle is the same. Cross enough invisible lines, and the planet starts doing the rest of the work for itself. The incredible part was how long Mars stayed geologically active while its surface climate slid toward extinction. Rivers carved channels, volcanoes erupted. For a while, the planet looked alive from orbit, even as its long-term habitability was being quietly dismantled. That is the lesson hiding in the red dust. Planets do not owe their inhabitants a stable climate forever. Mars is a cautionary tale that shows how a world can move from ocean-bearing to airless without any intention, just physics and time. The disturbing question now is how close a living planet can drift toward those same tipping points before the change becomes permanent. Because if Mars is the afterimage, the next step is to ask what early warning signs look like on a world that has not lost yet, and whether anyone notices in time. Mars, the warning, is also Mars, the unknown. For all the talk of it as a finished cautionary tale, the disturbing truth is that the story on that planet is full of blank chapters. The first is the most uncomfortable. No one can say with confidence whether life ever started there in the first place. Ancient riverbeds and possible shorelines show that water was once stable on the surface. In other words, the basic stage for biology existed, but there are no fossil mats, no clear microbial textures in rocks, nothing that would count as a definitive Martian biosignature. The scary part is that the second question is even more unsettling. If life did begin on Mars, did any of it survive? Buried microbes, frozen spores, thin layers of biology hiding under rocks or deep in the crust would change everything about how landers, drills, and future habitats are allowed to operate. Every scoop of soil becomes a potential contamination event in both directions. Hovering over all of this is a single simple molecule: methane. Small seasonal spikes have been detected in the Martian atmosphere for a while now. On Earth, that gas is often linked to biology, but it can also come from geological processes. The result was a decade of conflicting measurements, unexplained bursts, and no agreed source. Here is where things get uncomfortable. Without knowing what is making that methane, it is impossible to say what is actually being disturbed when the ground is drilled or heated. Beneath the surface, the uncertainties grow. Mars once had a magnetic field strong enough to shield an atmosphere and oceans. The exact timeline of how that field switched off and how fast the atmosphere bled away is still debated. That missing chronology is not just academic, it defines how quickly a planet can cross from habitable to hostile. The same is true for water. Radar hints at buried ice sheets and maybe briny pockets. Seismic data from recent Marsquakes suggest a complex interior, not fully frozen, not fully dead. But the total volume of subsurface water and where it is safe or possible to reach remains unknown. A wrong assumption here could strand future crews above rock that cannot sustain them. Then there is the human body. Long-term radiation exposure on Mars is projected, modeled, estimated, but never truly tested. Partial gravity at about 1/3 of Earth's pulls on bones, hearts, and brains in ways that are still guesses. Closed habitats will become sealed ecosystems where microbes, chemicals, and stressed humans interact for years. What would have happened on Mir with another decade of fungal evolution is an open question. On Mars, that experiment would be running on a whole world. The incredible part was that every unknown feeds directly into ethics. Is it acceptable to terraform a planet that might still shelter native microbes? Is it responsible to send colonists into an environment whose slow effects on the mind and body are not fully mapped? For all the orbiters, rovers, and landers, Mars remains more mystery than map. And the most disturbing questions are not about what has been found there, but about what has not been found yet, and what is waiting behind the first human footprint. Because the next step is not another robot. It is a decision about who goes first, what they are allowed to change, and what happens if Mars starts changing them back. That decision feels urgent. Mars does not share that feeling. From its side of the silence, nothing is rushing. The planet turns once every 24 hours and 37 minutes, dragging a thin, cold atmosphere through a sky the color of dried blood. Dust lifts, hangs, and falls again in slow motion. For a while, a single grain might travel hundreds of kilometers before it finally settles into a dune that will not move again for centuries. The scary part is, this is what passes for change on Mars. Ice creeps and retreats at the poles in seasons that repeat with mechanical precision. White caps grow in the dark of winter, then thin and fracture in the pale summer light. It looks almost gentle from orbit. In other words, it mimics the breathing of a world that is already gone. Rocks sit where they were dropped by ancient floods that no longer exist. Wind works on them with microscopic teeth, shaving them down over millions of years. The result was the landscape seen in rover images: rounded pebbles, carved layers, and hills that look as if they were frozen in the middle of collapsing. Everything is mid-fall, but the fall is stretched across geological time. Against that, human plans arrive like static. Launch windows measured in weeks, funding cycles measured in election years, careers and then entire lives measured in decades. Engineers argue about what would have happened if a trajectory had been slightly different. Mission planners worry about a single missed signal. Mars does not notice any of it. Here is where things get uncomfortable. From the planet's perspective, the Mars Climate Orbiter did not fail in 1999. A small, bright object brushed the upper atmosphere, turned to plasma, and its atoms joined the dust. The Opportunity rover did not die in 2018. A storm thickened, the light dimmed, and one more dark stone fell silent on the plains. For scientists, these are disturbing events, hard lessons, emotional losses. For Mars, they are weather. The incredible part was that this indifference is not hostile. The planet is not trying to kill anything. It simply is what it is: beautiful at a distance, lethal up close, and almost completely unchanging on human timescales. Radiation pours down because there is no magnetic shield. Perchlorate dust waits in the soil, ready to burn lungs and disrupt thyroids if it ever finds a way inside a human body. In a sense, Mars has already cast its vote on human presence. It voted by freezing its oceans, thinning its air, and letting its sky fill with unfiltered cosmic rays. It voted by making survival possible, but never easy, and never safe for long. The thing is, that vote will not change. Whether one person steps onto the surface or a million follow, the storms will still come, the ice will still grow and shrink, and the rocks will still weather in silence. So the question hanging over every blueprint and every launch pad is simple and disturbing. Against a planet that does not care at all, how much does human drama actually matter? The next part of this story begins when someone decides to answer that anyway. Someone already tried to answer it many times. The result was a planet quietly turning into a graveyard, orbiters that never spoke, landers that hit too hard, rovers that went dark in the middle of a storm. Over a third of all missions sent toward Mars have failed, enough that engineers half jokingly named an imaginary predator there the Great Galactic Ghoul. The thing is, from the surface, that joke looks more like an epitaph. Wreckage is scattered across dunes and crater rims. The Mars Climate Orbiter burned up in 1999 because one team used metric units and another used imperial. A simple mismatch. A $125 million fireball. Opportunity designed for 90 days wandered for nearly 15 years before a global dust storm smothered its solar panels and turned its last message into a memorial. In other words, Mars has been quietly consuming human effort for decades. Beneath that graveyard is an older one, a whole climate that died. Satellite maps show dry deltas, ancient shorelines, and minerals that only form in standing water. For a while, Mars had rivers, lakes, maybe even oceans, wrapped in a thicker atmosphere and a sky that could actually scatter blue. Then its magnetic field collapsed. The solar wind stripped its air, and the oceans bled off into space or froze into the ground. The scary part is what that implies. If anything ever started there, it had to face a planet that literally lost its sky. That history feeds directly into the disturbing future being planned for it. On the surface, radiation levels are high enough that long-term settlers would be gambling with their DNA every time they stepped outside shielding. The dust is laced with perchlorates, chemicals that can disrupt human thyroid function and poison closed life support systems. Low gravity would quietly erode bones and strain hearts over years. Add months of darkness, confinement, and the knowledge that help is millions of kilometers away, and psychological isolation becomes its own slow, invisible atmosphere. Here is where things get uncomfortable. Casualties would not be an accident of Mars exploration. They would be built into the design, and yet the planet keeps whispering back just enough mystery to hold attention. Seasonal methane spikes appear in the data, then fade. On Earth, methane often means life. On Mars, scientists have no clear source. Microbes? Geology? Something else entirely. Strange sounds recorded by landers. Thin winds, low-frequency rumbles turn a silent red postcard into an eerie living soundscape. Visual illusions in the rocks trigger faces, ruins, even animals where none exist. The incredible part was how quickly the human brain tries to repopulate a dead world. All of that feeds into the most disturbing question of all. Terraforming proposals talk about thickening the air, melting the ice, waking the planet back up. But is that exploration, or is it rehearsal, running the same experiment of domination on a new stage and hoping for a different ending? If Mars is a warning label written across a whole world, what would have happened if that warning is ignored? The next phase of this story begins when someone decides to go anyway and discovers what that actually costs. For a while, that decision sounded heroic. Go anyway, plant a flag on the warning label itself. But here's where things get uncomfortable. What if Mars never answers back? Not in radio signals, not in fossils, not even in a smear of strange chemistry that cannot be explained away as rock and sunlight. Just red dust, dead craters, and the wreckage of machines that tried to ask the same question and fell silent first. Engineers already have a name for this. Mars as a graveyard of missions. The Great Galactic Ghoul, that has swallowed more than a third of everything sent its way. Orbiters that vanished behind the planet and never reappeared. Landers like Beagle 2 that touched down and then went dark forever. The surface, in other words, is already a quiet museum of human failure. The scary part is that silence might go much deeper than broken hardware. For decades, evidence has stacked up that Mars once had thick air and oceans, river valleys that look disturbingly familiar, minerals that only form in standing water. Yet every rover that drills, scrapes, and scans the ground finds the same thing: chemistry that hints and retreats, patterns that almost look biological and then dissolve under closer inspection. Eventually, a more unsettling possibility appears. What if there was never anything to find? What if life is not just rare, but almost impossible? And Earth is the exception that slipped through a cosmic filter that closes on nearly every other world? If that is true, Mars becomes a mirror of absence, a whole planet saying without words that the universe does not care if anything can think or feel or remember. That is one version of the silence. But scientists are forced to consider another: that maybe the search has been looking in the wrong places, at the wrong times, with the wrong assumptions. Methane that flickers in and out of the atmosphere without a clear source, strange seasonal patterns in the soil, tiny details that might be biology or might be geology pretending very convincingly. In that version, the silence is not an answer. It is a delay. Something is there, but hidden under radiation-burned rocks, deep brines, or chemistry that does not match anything on Earth. And the result was a different kind of threat. If life is found, even as a fossil smear in ancient clay, then the idea of being unique collapses overnight. The incredible part was how quickly everything would have to be rethought. Ethics, contamination, ownership, responsibility to something that is not from Earth but is not just a resource either. Every future colony becomes a negotiation with an alien past or an alien present. So Mars stays quiet, and the planet turns into a kind of cosmic Rorschach test. Some see a lifeless desert and feel relief. Others see the same desert and feel dread. Which is more disturbing? A universe where this is the only place that ever woke up, or one where something else has already been watching from the dark? Colonists can't stay on the surface. Radiation forces them underground. But even underground isn't safe. Cosmic rays penetrate to 2 meters underground on Mars due to the thin atmosphere, meaning a standard 1-meter regolith roof provides almost no protection. Compare that to Earth, where 10 centimeters of shielding blocks most cosmic rays. On Mars, a habitat needs 3+ meters of regolith overhead to achieve Earth-equivalent protection. That's not a ceiling. That's a bunker. A colonist doesn't live on Mars. They live buried under Mars. The next step in this story depends on which answer is more frightening and who is willing to act on that fear. This is the moment to turn that discomfort into attention, because the story of Mars is not finished, and the scary part is that the most dangerous chapters have not even started yet. They begin the first day a real settlement tries to survive a Martian winter without a rescue ship on standby. Galactic Ghoul, and launched anyway. Anyone who still talks about Mars as a romantic escape probably needs to see that record. Sharing this video with them turns the fantasy into a reality check. In other words, it moves the conversation from posters and movie trailers to radiation dosimeters, pressure leaks, and supply chains that break if one launch window is